All right, hell yeah. So we have physics for scientists and engineers. You know what I mean? This is volume 1. This would be a engineering freshman level college course you would take. But you just won't do these problems. You know what I mean? These are the red star problems in the books. That's why it's red. And so this is the chapter 4 on projectile. It's two-dimensional motion. You know, motion in 2 dimensions. Now the take-home point here, though, huge thing is just like acceleration has to be constant. You know what I mean? And so it doesn't work for any problems where you're actually, if you're at a stop sign with your car and then you're getting up to speed, well, if you're at a stop sign, hell, you know, you don't accelerate, you know what I mean, at the same speed. You know, you might accelerate really fast, you know what I mean, and then once you get up to like 20 miles an hour, you might be slowing down to 25. So you're in driving a car, your acceleration, that's just your change in velocity, change in time. That change in velocity over like intervals of time varies quite a bit. So this is why we do projectile stuff, because the acceleration due to gravity is always a constant. And anything that's flying through the air, like horizontally, isn't affected by any acceleration, so that velocity will be the same. But here's the equations that get derived in the book, and I just never liked equations like this. You know what I mean? There's probably more equations like this with motion and particle motion. But if you don't derive these from the calculus or from using the differential equations and separating variables, I think it's actually less intuitive just to be like, well, you know what I mean, here's the equation. You know, if you have an initial velocity, here's your velocity final in the x direction. And so, okay, let's go over this. So we do have two things. We have acceleration in the y is negative 9.8, you know, meters per second. You know, we derive that from F equals ma. You know, we say we have a chunk of mass and we have an earth underneath us, and so this side of the equation is force of gravity. This side of the equation is the mass that we're interested in, and this is the acceleration that we observe. And force of gravity is gravitational constant m1 mass of the earth divided by the radius of the earth squared. So we jam that into this side, and we still keep this mass the same, and we just want to observe what the acceleration is. So we'll do this, you know what I mean? Because I think you should do this every time, because if you don't, you'll lose the fundamental understanding of where where this 9.8 comes from. I mean, basically, gravity is negative 9.8. So now we're saying the acceleration in the y is just g. You know what I mean? So that's where this comes from, and we're going to do it right here. F equals ma, so we have that force of gravity. Now again, the forces go on this side, and then we're analyzing that mass, and we want to know its acceleration. Well, this is m1. m1 cancels, and now we have an equation for acceleration. Now if m1 didn't cancel, well, you would just divide by m1, and then it would be whatever the the force, and you would get this force, out of a book, whether it was air resistance or viscosity due to water that has a resistance due to the velocity. But anyway, that's this side of the equation. And if you wanted to find the acceleration of that mass you're interested in, well, then you just divide by that mass. And only in the case of gravity, it just happens that the masses cancel, so the acceleration due to any object near the surface of the Earth isn't affected by it's not a function of its mass, but it is a function, gravitational constant, mass of the Earth, radius of the Earth squared. Alright, so now we can, and if you plug these numbers into your calculator, I'll do it right now. It's 6.667 times 10 to the negative 11, that's g. I can store that as g. And then we have mass of the Earth, that's 5.94 times 10 to the 24. Store that as alpha e. And some of these numbers you just memorize. 6.37 times 10 to the 6 is radius of the Earth. We're going to store that as alpha r. And then we got alpha g, alpha e, and then divided by alpha r squared. And we get 9.759, basically 9.8, rounded it to 9.8. So there you go. And I would look up on Wiki the exact numbers for these. But yeah, it's always just a little bit less than 9.8. I always thought that was kind of interesting. But then if you're at any height, if you're on top of Everest, it's going to be 9.8, something. It's going to be over 9.8. All right. So this says that the acceleration, and this thing is just gravity. So we say the acceleration on that mass, and we have to pick the direction. It's only in this y direction, is equal to g. So hell yeah, that's where that comes from. Booyah. And then the same thing is like, well, is there acceleration in the x direction? Is like, no, because there's not a big mass over here. There's not an Earth over here or an Earth over here. There is no gravitational forces sideways. So it's literally, I take the example of anytime you do a free body diagram, chop this thing and then just put it into like really deep space, away from all the stars. And what we observe is that we have a velocity, this way. And then it's a projectile, so maybe we do have a velocity in the x. We do have a velocity in the x that way. So if you take that system and put it into deep space and there's no forces acting on it, it'll just keep going that direction forever. So that's one of Newton's laws. And you bring it back to the Earth, and it's just amazing how, there is no forces pulling it this way. There is no forces trying to resist it this way and changing its velocity back that way. If I can identify a force in this x direction, then you must have acceleration. And if you don't have acceleration, but you do have a force this way, well, you must have an equal and opposite force. If you hook this thing to a bungee cord and then attach it to a building, and then you just induced a force that way, well, guess what? By observation. So this F equals ma, I always put eyeballs on this side, because, hey, in that case with the bungee cord, you observe that this thing's doesn't have any velocity that way, and is definitely not accelerating across the universe that way. So there must be another force this way, because the only way to get the acceleration to zero is if these forces cancel each other out. So that's F equals ma in a nutshell. And so now, and then we just observed that acceleration in the x direction is 0. So, even with these equations, anywhere where you have acceleration in the x, this just becomes 0 for most of your problems. For most all your projectile problems. So now you just have the velocity in the x is just the initial velocity. Nothing is changing its velocity. Where the velocity in the y, hell yeah, the acceleration is changing its velocity, and that gets us to our first equation. That acceleration, literally the definition of it is change in velocity, change in time. And this is where, and if you type it like this is great, because that's acceleration is like, well, at any little chunk of time, like t2 minus t1, and even that's too much, just writing these out, but just like, hell yeah, you have a little change in time, you're going to have change in velocity at this. And it's a constant, so it doesn't matter if it's between 0 and 1 second, my velocity is going to change in the negative direction by 9.8, So if I just jump off a cliff, hey, my velocity is 0, but guess what? In 1 second, my velocity is going to be negative 9.8 meters per second, because the acceleration is meters per second per second. And if you write it like this, instead of negative 9.8 meters per second squared, now you can see how it is like the units are the equation. Negative 9.8 meters per second, there's velocity every second. So, and this is by definition, this is your change in velocity right there, every change in t, for every, and then if it's just a base unit of seconds, we're just saying for every 1 second. So if I wanted to have a change in t of 2 seconds, guess what? We're going to have double this upstairs. So we're going to have 20 minus 0.4, so 19.6. So negative 19.6 meters per second. And the negative just says, hey, we have velocity in the negative y direction. And this is going to be the positive y direction. And this is going to be the positive x direction. Okay, hell yeah. So so this equation changing, so it'd be velocity 2 minus velocity 1. And then we said, hey, at 1 second we are negative 9.8. So now we can have an equation for accelerate. You can just work backwards. So we're going to have negative 9.8 minus 0 divided by 1 second minus 0. And guess what? Negative 9.8. And you can do that at any of those points. And because acceleration is a constant, you don't... You could take the time 0 and then the time final of hitting the water, and still you know, if you had a radar gun, you would be like, okay, we're going like 40. What do you impact? I think you go like 55 miles an hour divided by 2.25. Yeah, so maybe you're going 24 meters per second, hitting the water. Well, your initial velocity was 0. Your change in velocity is 24 meters per second. And then your change in time, let's say we clocked that as well. We had a radar gun and then we clocked it. And I got to do some quick mental math. So I would take this 24 divided by negative 9.8, or I mean just 9.8. But my change in time would be 2.445 seconds. So let's do this one. So let's find our acceleration. Is a change in velocity of 24 meters per second divided by 2.45 seconds. So 24 divided by 2.45, and we get, and I guess, oh, my bad. So my velocity right here is we're going to say is negative 24 meters per second. So we got negative 24 meters per second divided by 2, and we get negative 9.8. You know, we get back to that acceleration. But if our acceleration was changing, well, you can't just take the time initial, time final. You know what I mean? And you would get the average acceleration. You know what I mean? For some problems, if it's like a ramp like this, you at the bottom you don't have any acceleration in the y direction. You know what I mean? But right at the top of the ramp, hell yeah, you have all acceleration in the y direction. And then so if you found the time components, you know what I mean? Hey, your average acceleration it would be wrong because it's not a linear ramp. This kind of ramp's not linear, and so just keep that in mind if you do not have a constant acceleration in your path length. Okay, hell yeah. So now we got back here, so we can turn this into a differential equation. We can say, hey, it's the change in velocity, change in time with dv dt, and that just means we're taking a small snippet. But even this, like, who cares? Don't even pretend like you're taking a small snippet, because if you take bigger chunks, well, you're not going to get the most accurate answer, but you're still going to get close. You're going to get the most accurate answer if you take the smallest, most infinitesimal snippet. You know what I mean? And even a calculator can only go 10 digits deep, so even that's a limit on the snippets that you can take. Your change in time, you know what I mean, can only be, you know, probably 10 to the negative. Well, yeah, I mean, does that make sense? If a calculator can only, a calculator can only hold 10 digits. So if you don't have a difference between 10 digits 1 and 10 digits another number like 2, if you don't have a difference between those digits, you know what I mean? This snippet for practical purposes, I always think, hell yeah, just even take 1 second and what's your change in velocity, and then just know that's an average. But anyway. But this is where you go from here, is you say your acceleration is negative 9.8, but that's also equal to dv dt. And so a good way to write it is just write this dv dt, just know that's acceleration, and then we're going to have negative 9.8. And so now we have a differential equation that says, if we change our velocity, bummer. You know, sometimes. Alright, so a differential equation, I'm trying to get used to them so I can explain them, you know what I mean? Because I swear people don't have a handle on differential equations. Even I don't have a 100% handle. But what I do know is that this is an equation. So if I say the easiest thing to do is just change my time. If I have a change in time between 0 and 1, that's going to be a change in time of 1 second. Then guess what? I throw that value in right here. This equation chisels me out a change in velocity. You know what I mean? So if I say, and then, so this is an equation with 3 parameters. So you can rearrange this equation any way you want. So let's do that. If I wanted to solve for change in velocity, I would go negative 9.8 dt, and just even in this form, what you'll see is, you'll see it in this form: change in velocity, negative 9.8, change in time. And this is official, especially if you're just kind of throwing in 0 to 1. This indicates very small snippets, but who cares? You know what I mean? Just think of it like this, and then we're going to have dv is negative 9.8, and my change in velocity, we're just going to do 1 second. So cool, I'm going to have a change in velocity of negative 9.8 meters per second. And the units on this is negative 9.8 meters per second. That's acceleration. Multiply by 1 second. Seconds cancel, and you're left with meters per second. And then do the same thing. dv is negative 9.8 dt, and do a dt of 2 seconds. So we're going to go dv is negative 9.8 times 2 seconds, and then we'll get dv is negative 19.6 meters per second. So cool. So this is the equation. The other thing that you can point out that's kind of interesting is this is a because what we're ultimately doing is wanting to separate the calculus part is, well, let's get dv over here and then dt over there. So then we'll have dv is equal to negative 9.8 dt. And in this case, you know what I mean, and maybe I am kind of wrong on this, probably not, but it was like, hey, this is a function of t to the 0. It's a function of x to the 0. You know what I mean? It's a function of velocity. Well, I don't know if it's a function of velocity to the 0. You know, I don't even know what I'm saying here, but mentally it helps me because, you know, I probably am wrong a little bit on this, because I think this equation would be just fine if you integrate. This is just a constant out here. So if I said dv divided by 9.8 is equal to dt and then integrated, well, let's do that. So then we're just going to have v divided by 9.8 is equal to t plus a constant. And what we're going to say here, I mean, it's the same. It's the same equation. And then when we throw in time is equal to 0, and this is going to be, let's say, in the y direction, we want to know our initial velocity in the y. And typically it's a projectile problem where you have a v initial, and then you do have some vy initial is going to be v initial, and then here's the angle, and then so here's the sine component. Sun is shining on the sine, and we get v initial sine theta. And then so at time 0, oh, this is interesting. Yeah, maybe you can't do it this way. So so maybe there is some wrong ways, but yeah, what I want to do is explore ways that you could make errors. But anyway, if you just separate variables and we'll go dv is equal to negative 9.8, and then I would just go t to the 0, because then we got dt. So, and then we're integrating this side, and I mean, would it make the same over here? But yeah, maybe what I'm doing right there is wrong. I don't know, actually. But then when we integrate this, we get v is equal to negative 9.8 t to the 0 plus 1 divided by 0 plus 1 plus a constant. And just for whatever reason, it just kind of works out nice, and we get negative 9.8 t. We need to figure out our constant, so that's where we throw in time is 0. Now what's our velocity? Our velocity in the y direction is going to be v initial sine theta. So we have a v initial sine theta, and this is going to be velocity in the y. And that's where if we go velocity in the y, we get this. We get our initial velocity, that's v initial sine theta, and then plus acceleration in the y times time. But when you integrate it, you actually write it this way and not that way. So even like writing it like this, I don't know, is a little bit confusing compared to just, doing the integration. So now we're going to do this, and then once you get to here, then you can say that velocity is just change in position, change in time. And we're in the y direction, so we got change in y, change in t. And then so we can say velocity in the y is dy dt. And then so now we have this equation for Vy. We're going to, I would write it like this, dy dt, and then, and then this would be Vy, and then so, but we know this is Vy, so we're going to throw it in right here, negative 9.8 t plus V initial sine theta. And now we can separate variables. So we're going to bring the dt up here and then integrate, and then we're going to get an equation for y, which is going to be negative. This is t to the 1, and so when we integrate it, it's going to go t to the 1 plus 1 divided by 1 plus 1, which is t to the 2 divided by 2. So now we're going to have negative 9.8 divided by 2, which is negative 4.9 t squared plus V initial sine theta, and then this is t to the 0. So we got t to the 0 plus 1 divided by 0 plus 1. So we basically get t to the 1. And then so we get that t right there, plus a constant. Now at time 0, you got to do that same thing. What's my position in the y? And for most problems, sometimes it's just 0, so then you do c is 0. That won't be the issue for our problem, because, so finally we're kind of going to read it. So we have a firework that goes up. It hits the top, so velocity is 0 at the top, and then it explodes sparks in all directions, downward, left, right, up, and then every direction in between. And so let's just pick one. Let's pick the one at a 45-degree angle. So that's the one that I was kind of interested in, theta 45. And so, and this is our height above the ground. So with this equation, at time is equal to 0, and we're going to say, hey, that's and then we can put the origin down here. You know what I mean? And then so we can say this height at time is equal to 0 is equal to h. And then so c is equal to h in that case. But if you move the origin over here, you can be like, well, this direction is h, but it's in the negative y direction. Then at time is equal to 0. Well, if you started there, you're right at your origin. So then c would be equal to 0. Okay, hell yeah. So that's kind of the basis there. And if we look at this y equation, so we have, and this is kind of y final. And why it's y final is because at any given t, if you're just doing a t of 1 second, well, that's going to be your final y at 1 second. You know what I mean? So I think it's even kind of not useful to call this y final, because depending on what time frame you're using, because you might use a different time to solve this equation than you would to solve this equation. You know, sometimes different things happen at different times in a projectile's path that you're interested in, whether it's the peak, whether it's trying to get over a mountain, whether it's to land. You know what I mean? That's 3 different times right there. And so that's the only thing to keep in mind, that these equations, this y final is only equal to this x final if these 2 times are the same. So keep that in mind. Okay, so but now we have this y is equal to, half the acceleration. Our acceleration of the y is just negative 9.8, so that's where we get negative 4.9 t squared, plus our velocity in the y direction. And this shoot, I shouldn't have, this says initial, so that was that v initial sine theta, and then and plus our position in the y. So yeah, if our origin is down here, that's going to be h for our problem. Okay, hell yeah. And then if we go back and do the same thing for the acceleration in the x direction, now we're going to have dv dt is equal to 0, and alright, hell yeah. So we have acceleration in the x is 0, so that means our acceleration is that differential equation, change in v, change in t. And just because it's a differential equation, you know what I mean, that means that you do the changes, you know what I mean. So if you observe a velocity here and then a velocity there, that's going to, you can figure out that change in velocity. And then if you know the time between those 2 points, well hell yeah, then you know that's going to equal 0. And if you already know this is equal to 0, then you can be like, well, I do know the time change. You know what I mean? I do know I'm going to take a time between 0 and then maybe like 10 seconds to splat or something. And so what's my change in velocity? And in this case, my change in velocity will be 0. So if I had an initial velocity, well, it's just going to be the same. So treating this like an equation, even though it's a differential, you know what I mean? Circle the 3 things that you know, and then you can rearrange the equation any way you want. So we're gonna do the same thing, separate variables, and we're gonna get dv is 0 dt. When we integrate, still I can do that same trick and call this 0 times t to the 0. And when I integrate that, I get 0 t to the 0 plus 1 divided by 0 plus 1. So I do get 0 times t to the 1, but guess what? Multiplied by 0, that's just 0 anyway. And then so all we're left with is a constant. This side is velocity. So after integrating acceleration in the x, we get velocity in the x is equal to a constant. And then this is still, and you can still do this equation. You can be like velocity in the x is equal to 0 times t to the 1 plus a constant. So when we throw in a time value of t is equal to 0, you know what I mean? Well, we're going to have 0 times 0 to the 1. Well, obviously all this crap is 0, but it at least visually gives you that indication that we still need to find our constant of integration, and we do that at evaluating at time is equal to 0, and we can see that velocity in the x, if we had any, is just the initial velocity in the x. So we go over here to our velocity in the x equation, and this is an equation for, sorry, I shouldn't have done that with the x, but this is an equation for velocity in the x as a function of time is going to be, in our case of our projectile is going to be v initial cosine theta. Well, cool. It's a function of time, but guess what? The time value, let's write it again, after we integrated it, it's going to be Vx as a function of time is equal to 0 t to the 1 plus V initial cosine theta. And then this actually comes out in this equation. Because if we go up here, we're going to have Vx of t is equal to V initial, which is, Vx, the initial velocity in the x direction, V initial cosine theta, and now we're going to go plus negative 9.8. I'm sorry. Our acceleration in the x is 0, so we're going to have plus 0 times t to the 1. So you still have that. You have exactly what we wrote. I don't want to grab another sheet of paper because we're just talking through it. That's what I want to get used to, is just like talking through the problems where, writing it down is not the issue. It's verbally explaining it, 1,000 times so it sinks in. So now, so you have that. This is 0 t to the 1. So obviously the velocity in the x is a function of time, kinda, but it's kinda, but kinda not. But this is, but yes, it is a function of time. It's a function of time, but the equation is 0 t to the 1. You know what I mean? So I still think it's, I need to research that, but I still do think it's totally okay to say, hey, this is negative 9.8 t to the 0, and for that same basis to learn the other, aspects of differentiating with other things, is the same thing as also t of x to the 0. You know what I mean? And potentially, but anyway. Okay, so hell yeah. So that's where these equations come from, is starting with negative 9.8, integrating, starting with x is equal to 0, integrating. So now we have that Vx is equal to V initial cosine theta, and now we want to do the same thing and find position in the x. So we know that velocity is just change in position, change in time. Now we can say that's equal to V initial cosine theta. We're going to separate variables, and this is going to be dx dt. So now we're going to have dx is velocity initial cosine theta dt, and now we can integrate. Dx becomes x, and the integration of this goes to V initial cosine theta and then t. Because this is t to the 1, but you could also say this is t to the 0. You know what I mean? So you could still do that. And visually, it'll make, I think it'll make more mental sense when you know that, especially when you're integrating with respect to a change in time, that you're like, well, I don't see a t here. But yes, it's going to be t to the 0, integrate that, t to the 0 plus 1 divided by 0 plus 1. And then you get t to the 1 for this x term. And if we go to our equation in the x, well, yeah, this becomes 0, and now we'll just have the initial velocity. Sorry, we do have a constant here. So we do have a constant. So then you have to evaluate. At time is equal to 0, what's my x direction? So if we set, so even with this firework, even if we set the origin down here, which we will, our x direction at time of explosion for a firework that goes straight up is just 0. So this will be our equation for the firework. Now this is a red star problem, and what I'm envisioning is that they want a firecracker that goes straight up in the air. If I have time and I want to make this like a 4-hour endeavor, what I want to do is also do a firework that had an initial theta. You know what I mean? So we're going to say any initial theta, and then it's going to have a, because obviously the, well, no, we probably won't do that, because this problem is set up where if we go straight up, we already know its initial velocity. You know what I mean? Because we already say it reaches a max height of h, and so now we're going to actually start in and start solving this one. Okay, so we have I think it's worded kind of tricky, but a firework rocket explodes at height h. I'm just going to assume straight up. The peak of its vertical, and that's at the peak of its vertical trajectory. It throws out burning fragments in all directions, but all at the same speed. Cool. Pellets of the solidified metal fall to the ground. So they burst with an initial velocity once they do vi, and then those metal pieces fall to the ground without air resistance. And then this part was confusing. Find the smallest angle that the final velocity of impact fragments make with the horizontal. This is the first thing I did to actually get that. Is like, well, let's say there was no ground and one of these fireworks just blew up on the surface. You know, so there's many ways to make the problem, you know what I mean, actually make sense. And this was the first one, because not only do I know that the projectile that's going to go the farthest if this explodes on the ground is the burning fragment that's at a 45-degree angle, because I know that about projectiles. This can get you the farthest distance. And if I now read, because I was just like, well, it's just like if it blows up straight up, aren't the particles that go straight up or straight down going to land right there, and that's going to be the smallest angle? You know what I mean? I was considering my angle this way, but no. They say smallest angle that the final velocity of an impacting fragment makes with the horizontal. So I can say, hey, what about this angle? Is that made from the horizontal? No, this angle is made from the vertical. So if we say this is the horizontal, this is the angle that is made from the horizontal. If I say this is the horizontal, I can say that this, if this is the vertical, I can say that this is the angle right here, phi, that's made with the vertical. So this is the angle that they're concerned with, and they want to know the smallest. And so, and this is good, because even if that was the case, I was just like, well, isn't it a 45-degree angle? You know what I mean? Like, just from that aspect, even if it's at height, doesn't a 45-degree angle go the farthest? And isn't the farthest particle the one that causes the shallowest angle? Now, one of those statements might be correct, but the other one is not. If you do have an elevation, we just did the ski jumper problem that we have a slope like this. And then if we have a slope phi, the max angle right here is going to be phi divided by 2, 45 minus that. So we know that if this angle is just horizontal and then phi is 0, if phi is 0 and we have a horizontal, it's just going to be 45. But the second we drop off where crap can land lower, you know what I mean? Then we have to figure out where it's going to land, and then figure out the angle from where we exploded that firecracker to that landing point. You know, that phi is going to now the farthest distance. So if that's our case, and we exploded a firecracker, and we say, whoa, we got a metal pellet out here, you know what I mean? And then be like, whoa, and we know that this is a height of like 210 feet, and then we could figure out the feet of this, and then we could figure out this angle. And if we did that, then we could say, and let's say this angle was just 35 degrees, 35, just like our ski jump. So we do 35 divided by 2, and then we go 45 minus that, and we get an angle of 27.5. It's the particle of molten fragment that had an angle of 27.5 that caused the smallest angle with the ground. You know what I mean? Or in this case, got the farthest. You know what I mean? Let's say that fragment actually got to there. Now, phi isn't the answer, because that's the other thing, not to mess up the question. It says, find the smallest angle that the final velocity of an impacting fragment makes with the horizontal. So if its path comes down like right here, then its angle with the horizontal is this. You know what I mean? So this is the angle that we want. Maybe like theta prime. So we're interested in theta prime. We have a theta initial up here. So yeah, so based on those things, you know what I mean? So that's where this problem, I think, becomes tricky, because you're from the ski jump problem, it's the total the ski jump problem, but we just don't know. We don't know what the farthest particle is, and so the first place to start with this that I thought, just so we make sure we get the right answer in the end, because also this problem has no numbers on it. We are totally just working with variables. So that's the first thing that I'm going to do is throw some variables at this. And I researched online that if we have a 3-inch mortar, coming out of the tube, some of the bigger ones, you can get 210 feet. So let's go 210 feet. Factor label method, we go 1 foot below because we can cancel that. That's going to be 12 inches. We can go 1 inch is 25.4 millimeters, and then 1,000 millimeters is 1 meter. So we do all that jazz. And, if you don't want to mess this up, 210 feet divided by what? About 3. This should be about 70, probably a little bit less. So 210 times 12 times 25.4 divided by 1,000. And whoops, see, even right there, I made a mistake. I divided by 100. So that's why you always we're shooting for about 70, and then so we're going to do that same thing divided by 1,000, a little bit less. So, anytime that you do like a math equation where you're just like, whoa, this is too much, there's too many things going on here, this is like 4 places to make mistakes. And so we're going to store that. So this is going to be our height, so we're going to store that as alpha h. So we have 64 meters basically. And then I went online and said, hey, 1,000 feet per second is the velocity of an exploding mortar. The particles in the mortar, once they blow up at height, you know what I mean, they will go 1,000 feet per second. So cool. And yeah, that's interesting, because you're just like, when you see the color flash, you know what I mean, that's just after it explodes at 1,000 feet per second, and then the secondary stuff lights up. But you know what I mean, and then those will also have a secondary. But let's say you at height, this thing just explodes at 1,000 feet per second, and then you just had like LED lights that lit up to show you the firework display. Well, it would just keep on going. What you don't see is that those things are still traveling at that 1,000 feet per second, at least sideways. You know what I mean, and then faster because they're getting accelerated down to the ground. So that's what you don't see, because the lights of a firework don't stay on forever. Okay, so that puts some parameters on it. We have 1,000 feet per second. So let's do the factor label method on this so we don't mess up. We're gonna go 1 foot and 1,000 feet. 1,000 feet per second. You know, I mean, we need something. You know, how many feet in a mile? So this is almost like a, you know, it'd be 5,000. So that would be 1 mile every 5 seconds. Cool. So now now we have some parameters. And one mile a second, you know, 1 mile per second. Holy Toledo! I think I just know this is around like 700 to 1,000 miles per hour. No, 1 mile a second, a mile a second. Yeah. How many miles? No, that would be 3,600 miles per hour. Because if you're going a mile a second, how many seconds are in an hour? 3,600. So even just right here, if we're going, but we're going to go 1 mile every 5 seconds. So we're just going to do 3,600 divided by 5. So hell yeah, I think we're going to go 720 miles per hour. But this is cool because this is the stuff that I want people to do, and I want myself to do this. Because even right now I have another factor label method. I might mess this up. It's just another place to make little errors. So right now I just want to know what the hell is 1,000 feet per second? Well, it's 720 miles per hour. And so there we go. I knew it's like a factor of like 1.4 or 1.5. I just wouldn't know. It's like, is it 1,000 divided by 1.5? Is that or 1,000 divided by 1.4? You know what I mean? So if it is a factor of 1.4, do I take 1,000 feet per second? So that's the question in my mind. Is 1 foot oh yeah, one is what am I getting at? Wait, 1,000 feet per second. Yeah. No, that's 100% right. 1 foot per second. How many is it? Or 1 mile per 1 hour? What is bigger? You know what I mean? If I go 1 feet per second, or if I go 1 mile an hour. So now this is a good one because I would do these in separate videos. You know, but that separate video would have to be like 4 hours long, I swear to God. So that's why we just do it on the fly. So if I'm walking, you can visualize the speed of walking 1 foot per second. That's hella slow, you know what I mean? So even just that 1 foot a second, be like, come on, man. You know what I mean? Pick it up. Like, because like you can take a step about every second. 0, 1, 2, 3, 4. You know what I mean? That's a slow walking pace. And if you are just walking 1 foot, I mean, the average stride is at least 2 feet, even at like Eeyore speed. And so 1 foot per second is like, hell yeah, come on, man. And 1 mile an hour, well, obviously 1 mile an hour is a pretty slow pace to walk. If you're only walking 1 mile in an hour, you're also walking pretty damn slow. So now I guess it doesn't help me, but what's going to be slower, 1 foot a second or 1 mile an hour? Because even, I think we got 1 mile an hour, even on a hard trail where you're just like, oh, this trail is going to take me 1 mile in an hour. I still think this is going to be faster than 1 foot a second. But if I totally messed up on that scenario, at least we know these are about equal, you know what I mean? So there you go. So my answer should be at least within a ballpark of 1,000. So if it's 1,000 feet per second, I should be pretty close to 1,000 miles per hour. But I think I think this one is slower. So that means that if this, then you get into that game of like, well, if 1 foot a second is slower than 1 mile an hour, then 1 foot per second would be like, 0.7 miles per hour. You know what I mean? And that's what we're going to get. All right, hell yeah. Factor label method away. And we're going to go 1 foot is 12 inches. All right, so we have 12 inches, and then we got to go 1 inch, because we cross out feet, and then we can cross out inches, and 1 inch is equal to 25.4 millimeters. And what we're showing here is, hey, 12 inches is 1 foot, 25.4 millimeters is 1 inch, and now we'll go 1,000 millimeters is 1 meter, and those cancel. So now we're left with meters, but we're meters per second, you know what I mean? So now we got to take this seconds, and I'm just going to do it real fast. 3,600 seconds divided by 1 hour. You could go 60 seconds is 1 minute, and then 1 minute, and then 60 minutes is 1 hour, and then cancel those out. But hell yeah. So now we're going to get meters. Holy Toledo. So, we're going to get, oh, damn it, I apologize. You know what I mean? We're shooting, we're trying to get feet per second to miles per hour. My apologies. So, and not really. I mean, we actually want meters per second, but no, this is a good place to slow it down and show the factor label method. So, 1,000 feet per second, 1 foot is so if we want to go to miles, now we do 5,280 feet is 1 mile, and now we're gonna go. So now we have miles, but now we got to go. And I'll do that. I'll go. Hey, 60 seconds is 1 minute, and then I'll say 60 minutes is 1 hour. And as long as these minutes cancel this way, and then the seconds cancel that way, now we're left with miles per hour. Okay, so we got 1,000 divided by 5,280 times 60 times 60. And so we have 681.8 miles per hour. And it was right here that I was going to be like, well, if I knew the speed in meters per second, if I knew that speed, I do know that all I have to do is multiply by 2.25 to get miles per hour. You know what I mean? Hell yeah. But now we know the speed in miles per hour, so what we would do is divide by 2.25. So divide by 2.25, and so we're approximately 303 meters per second. But we are going to do factor label method, one more time. 1,000 feet per second, 1 foot is 12 inches. 1 inch is 25.4 millimeters. 1,000 millimeters is 1 meter. Cool. Those cancel, those cancel, those cancel. We're meters per second on this one. 1,000 times 12 times 25.4 divided by 1,000, and we get 304.8 meters per second. This is going to be our velocity initial of the pellets. So I'm going to store that as alpha v. So hell yeah, that's stored as alpha v. We have an initial height of 210 stored as alpha h. And so now we're on a roll. So we at least have a couple numbers in here. And so then we can, what I wanted to do was probably use Excel, but we wouldn't have to. We can just start throwing numbers at this. So we're going to get our equations, and let's see if we can get our equations fast. We have negative 9.8. That goes to negative 9.8 t plus a constant. When t is 0, we have a velocity in the y direction of v initial sine theta. So now what we're talking about is at the peak right here, we have an initial velocity of our particle and a theta, and so this is the velocity in the y equation. Now we can get a position equation in the y. It's negative 4.9 t squared plus v initial sine theta initial t. And where's our origin? We're going to put our origin down here, so we will have a height. Our initial height is h. Hell yeah. And then if we do that same thing for velocity in the x, we're not going to have a function of t because we're going to have 0 acceleration, and then you're just going to, when you integrate it, you're just going to have that constant. So it's just going to be velocity initial cosine theta, and then we have our position. Our position is just going to be velocity initial cosine theta of t plus a constant. So what's our position in the y when time is equal to 0? Well, at least our x position is x positive this way, but we are in line with 0x. So it's just, so that's it. So that's our equation for x. Here's our equation for the velocity in the x. Here's our equation for y, and here's our equation for velocity in the y. So the first thing that I want to do is analyze a couple scenarios. At the top of that explosion, I'm going to pick a 0 angle. You know what I mean? Because this is where, let's go back to this example, because if you can't see the solution from start to finish, then you have to ask yourself more questions. And I did before starting this video, and I just saw this probably about 30 minutes before starting the camera. This is the first time I've ever seen this problem. You know what I mean? So even me, I had to figure out, well, isn't it just 45? And then I was like, probably not. You know what I mean? So how do we prove that? Well, if this mortar explodes on the ground, well, hell yeah, a 45-degree angle is going to go the farthest, and that does create an angle. But is that the minimum angle? I was like, oh, hell no. You know what I mean? Because obviously there's going to be a particle that is less and it hits the ground early, or just like is almost horizontal and hits the ground almost horizontally, or the particles that literally just blast out horizontally hit the ground. That would be an angle min. You know what I mean? If this thing exploded on the ground. But the second explodes at some sort of height, so now our 45, well, we already know from the ski jump problem that our 45 isn't the best angle to get the farthest distance. You know, the 45 will lob up and then lob down. It's actually an angle less to get the farthest distance. And you can see that if we land short with too steep of an angle, hell yeah, that angle is real big. So that's going to be like a max angle. Where if we go the farthest distance, our angle is, now the question is that the minimum angle? And I don't know. Because let's say we went horizontally, we're not going to go the farthest, but is there a chance? Well, just from that reference, if we don't go the farthest, the parabolic path, won't it have to land? I don't know. You know what I mean? I don't think so, because this thing is right at the ground, and you would want the path that is totally perpendicular. So now let's just go up a little bit, and knowing that the path that's totally perpendicular will produce the less angle. You know, if we're on the ground, it's the spark that goes totally horizontally, if I said that right, and then hits the ground. But we see up here, I can't prove that. I can't prove it's the spark that goes perfectly horizontally and hits the ground, because even I think it's not the spark that actually has a lower angle. I think that would be worse. You know what I mean? So just visually, I think that would be worse. I get how if this spark was totally horizontal and hit the ground right here, but let's say I angled it up just a little bit, you would have more angle, and you would get more distance, and then it would start to fall. I don't know. You know what I mean? So that is the scenario that I don't know. I know a 45-degree angle is probably awful, but so we're going to do a couple. We're going to do an angle of 0 degrees. So just totally horizontal. Might as well do that, see where it lands, and then try to find that angle. And how we do that, how we find that angle, is like, well, we set up the equation to we know our h, and we know when we throw oh yeah, this is a bummer, because sometimes you want to flip the script and say, hey, this is the origin, and then we have a positive acceleration in the positive y direction. If we're going to call this positive y direction, and we set our origin there, this is kind of cool, because you know what I mean, you know, our particles will just go on forever, but they will hit a ceiling right here at h. So that I'll see if I want to totally flip the problem, but we'll do it this way. I mean, it's just a sign change, but I swear sometimes when the signs don't kind of match up mentally, it drives me absolutely insane. So we're going to do that one, and then we're going to do a 45, and then we'll do something kind of in between. So at a 0 degree angle. All right, hell yeah! I want to get this first example done before my camera starts to overheat. Okay, so we're going to be at some height, 0 degree angle, and now we want to know when it hits. So our y value, our equation for y is this, and sorry, so our origin is right here. You know what I mean? So if this is our origin, we want to know when y is equal to 0. So we take this equation and set it equal to 0. So let's do that. We got 0 is equal to negative 4.9 t squared plus v initial sine theta t plus h. And our h is, alpha h is going to be 64. So we got 64. Our v initial is alpha v, and that's 304.8. And then yeah, we're setting it at a y final. You know what I mean? From our original equation, you know what I mean? This is the y final. But I just like to think of it as an equation for y. You know what I mean? So, and then obviously, if we take the y value at 0, it's going to be the time at that value. It's going to be the time for that projectile to get to that location. Because this is an equation for the position of that projectile at any given time. Okay. Time's not in this axis. Time is like 0, time is equal to 1, time is equal to 2, time is equal to 3. You know what I mean? So that's kind of what that equation looks like. Alright, booyah. So we're going to go 0 is equal to negative 4.9 t squared plus 304.8. And then we're going to go sine of 0. Cool, so that's just 0 times t plus 64. So this one we don't, because that was the thing, is like I don't want to just graph everything and solve it with my solver. So we can see that sine of 0 is 0, so this is 0, and then we're going to bring this over here, so we're going to have 4.9 t squared is equal to 64, so we're going to have t squared is 64 divided by 4.9, or t is the square root of 64. So we got square root of 64 divided by 4.9, and I'm pretty confident in this. Time is equal to 3.6 seconds. I'm going to store that as alpha t, and now we have our first maybe check on reality is we can now find, we want to know this distance, because at the end of the day, how do we find the angle of impact? We find the angle, and maybe this isn't true. I was just assuming, holy Toledo, so I'm making a huge assumption here. I was going to assume that, no, this is not true. I was going to assume that this angle of this, which would be tangent of angle is h over x, would be my angle of impact. But no, that's hella not true, because it's the ski jumper problem. If you have a ski jumper and they're landing on this slope, and sure, they're going to land right there, but they're going to be impacting, they're not going to be at a perfectly, they're not going to be at the same angle as the slope. This is interesting. So we need a differential equation, and just saying that, it's like, well, like all these equations were integrations of each other, and so yeah, so I'm going to work my way mentally through, how do you find the slope at that point? Because if you found the slope at this point, and let's see if that makes sense. If I have an equation that's mx plus b, this is y is equal to mx plus b, but I'm going through the origin where I just have a slope of m, you know what I mean? So this is an equation of y is equal to mx, where the slope is rise over run. So we're going up m and then over 1. So there you go. And so that would that would mean that this is m, this is 1, and I would want to know maybe my angle right here. Well, my angle is going to be, angle theta is going to be m, tangent of the angle is m divided by 1. So then the angle is just inverse tangent of the slope. Okay, so if I knew the slope of this point right there, I would know the angle of impact. So yeah, so I'm glad I didn't mistakenly, just think the slope was this distance and this height, and then that angle, because that has nothing to do with the angle of impact. I mean, theoretically, given enough distance, or enough height, I mean, like all particles are going to be almost vertical, even though yeah, most of the particles can be fairly vertical, even though these distances, you know, are about a 45 degree, maybe a 45-degree angle from each other. Cool. All right, so I guess now what do we do? I mean, is it even valuable to find this? Like, and then what the hell did we just find? We just found the time to do that. Holy Toledo. But we do have a position equation. Oh, perfect. So let's say this. Yeah, let's do that. Let's at least find the x. So we have x is equal to velocity initial, which is 304.8, cosine theta initial, which is 0, so that's 1, times the time, 3.6. So now we're going to have an x of, well, hella, right? So we're going to have alpha v times cosine 0 times alpha t. So yep, and then 1,102 meters. Okay, so that's our x value. The y value was just the height, and that's just going to be h of 64. Alright, so the y value is just going to be 64 meters. So holy Toledo, even at 64 meters, these particles are going so fast that they're going to land hella far away. That's amazing. It's not too tall, but because of the speed of the burning fragments, like, whoa, they can travel hella far. So that is amazing. And we were saying those particles, and hopefully I got that right, 720 miles per hour from blowing up. I looked it up. I said artillery shell explosions, what's the speed of them? And they said 1,000 feet per second. But even right now, it's just like, well, I don't know. It's like that seems really far away. You know what I mean? 3,000. Like 1,600 meters is a mile. So we got 3/4 of a mile. A plume of firework fragments. But if you ever smell fireworks, you know what I mean, you're probably getting bombarded with the fragments and maybe just not the smoke involved. I don't know, you know what I mean. Okay, so I'm still at a head scratcher, but not really. So we at this time 3.6, we have a position of 304.8. What the hell am I even talking about? So we have a position of 1,002 meters and a y of, well, what am I even talking about? The y is 0. You know what I mean? So we already did that. Y is 0. So now I have a position. So this is what I'm going to do. This is the only way. I'm sure I can just take a friggin' derivative and be like, oh, no duh. But this is how I do things when you don't know how to do the calculus. You know what I mean? You don't need to know how to do the calculus to actually get the answer. Because right here we have our equation for this is 11,002 and 0. You know what I mean? In the x direction, 1102, 1,102 meters, and then 0 meters in the y direction. So what we want to do, and that's going to be at time is equal to 3.6 seconds. So alpha t. At 3.6, we're going to go time is equal to 3.5 seconds. You know what I mean? This will blow your mind. So now we're going to do the same thing. We're going to throw in, so we're going to go 3.5 stored as alpha s, and now we're going to get our y equation, negative 4.9 alpha s squared plus alpha v sine 0 alpha s plus alpha h. Hell yeah. So now we have so now this is our y. So our new y is 3.983 meters above the ground. I'm going to store that as alpha y. And then for our x, we have alpha v cosine of 0. That's just the initial velocity times time, which is alpha s. And we still have hella away, which is 1,066.8 meters. I'm going to store that as alpha x. And I need to go get the other one. This one I'm going to store as alpha d. So we have at impact we have d, and then just before impact, so this one's d, this is 0, and this is y in my calculator, and this is x in my calculator. So now we have 2 points, and we have one that says, hey, we're 0 and way the hell out, and the other one that says, well, Now we're not as so far out, but we're up 3. So what this says is we have 3.983 with the little triangle, and then this distance is the difference between them, so it's alpha d minus x. And then so we have 34.75 meters, and so that's hella. And then we need to find this angle. Well, the angle is so if we take tangent of this angle, that's going to be the sine over the cosine. And let's talk about this. So tangent theta, by definition, is like the sine component divided by the cosine component. And you've heard me enough say that if this is the angle, the sun is shining on the sine component, and the other component's the cosine. And if the other thing that I say is, hell, in a right triangle, the hypotenuse is always the bigger number. And then so what the hell are sine and cosines? You know what I mean? They're fractions of a whole. They're numbers between 0 and 1. And if we take the hypotenuse, the bigger number, and multiply by like 0.5 or like 0.866 or 0.707, all the popular sines and cosines, well, guess what? We're going to get a number that's less than the hypotenuse. And that is going to be these numbers. They're going to be slightly less. Cool. So then when we have this ratio of the sine component divided by the cosine component, and let's talk about this again. So if this is h and this is theta, this one is big number sine theta. This one is the hypotenuse, big number cosine theta. So if we want to get the tangent of the angle, well, it's this component, big number sine theta, divided by big number cosine theta. And now you can see how it's not a function of this part of the ratio cancels out, and you just have the fraction, between there and there. So hell yeah. So anytime you see the term tangent of an angle, it's opposite over adjacent, but it's the sine component divided by the cosine component. So hell yeah. So this is going to be sun is shining on the sine, 3.98 divided by 34 point whatever. And so which is also, we need to do that. So this is also just y minus 0, and this is alpha d minus x. So alpha d minus x is that 34, and then alpha y is the other one. So we're going to, and then so if that's tangent of the angle, we want to find the angle. So now we got to go inverse tangent of alpha y divided by d minus x. You know what I mean? The inverse tangent of 3.9 divided by 34. I can just do that. Inverse tangent of 3.9 divided by 34 is 6.5 degrees. So, and I feel like I did something wrong, you know what I mean? But it all comes down to this velocity being just super crazy, like a horizontal, like this really wild. I'll have to double check this number when my camera just overheats, and it's going to overheat in 30 seconds. Alright, so I'm going to catch you on the flip side. Alright, hell yeah. So we're back. I took a long break, and you know what I mean. So what we're and where we're at is we found 2 points, and so that gives us this triangle, because we'll have the point when it's 0 and at a far distance, and at a point x and here, and so we can find the theta. And what we did is we found that it was close to 6.54. We're going to get it exact, so we have alpha y is this, and that makes sense, divided by alpha d minus x. And so that's the ratio between those, and then inverse tangent of that answer. And we get, so I'm going to store that as alpha theta. So this is the theta at 45 degrees. Cool. And so it's theta is 6.5 degrees. Let's just say that. Oh, I might have misspoke. This is at 0 degrees with the total horizontal projectile. So now what we want to do, we'll probably overshoot it. That's what I'm thinking. If we go to 45, we might get an angle that's greater, but but now I kind of have an understanding of how to get the derivative. I thought I did. You know what I mean? To get the derivative at the point, so you know what I mean? Because we threw in an angle of 0, we got the time frame to do that at 3.6. We got the position x and y, and we wanted to know the derivative. And the derivative was just the slope of this line. And we can see that the slope of this line is rise over run. So if we start here, we go negative and then over. So we're going to have a slope of negative 3.9 divided by 34 point, whatever. So our slope is the y value divided by d minus x. So we're going to go alpha y divided by alpha d minus x. So that's our slope. I'm going to store that as m. So there you go. We have a slope of 0.11, and just know that its slope is rise over run, and so we can actually find the units on this. We're going to have 0.11 height divided by length. So it's height divided by length from that origin, or it's m is height of let's see, is just our y value divided by our x value. Whoa, that's not true. My apologize. Yeah, I apologize. Holy Toledo, I'm still confusing this height and this distance with that angle, and that's not the slope. The slope was, we had to find the time here and the time there, and then we knew. So so now what we're saying, at t equals 3.6 is like, well, what's the slope? And so the slope is the difference in the holy Toledo. I think I just need to say, I think it's the velocity equation. So the velocity equation in the y and the velocity equation in the x are the slopes at those 2 points. How does this work? So you have, we integrated. We said that v was d. This vy was dy dt. So that is the slope. The change in y with change in t. So now we have something where you have. So this is the other thing. Is like this is a graph of like x and y. But if we graph t as a function of y, then that's what this is. You know what I mean? So we'll have dy dt, and then the change in y with respect to t is the definition of velocity, and but we integrate to get an equation for y, and so at time 0 you're at the height, and then at time 3.6 you're here. So this is the equation for what we came up with. This is an equation with t of y. And what we're saying is we want to find the slope of this line. Well, if this is the equation y, the slope of a line is just the derivative of this equation. And the derivative of this equation is the vy. So I think that should do it. Hopefully that gives us the same. So we're going to throw in alpha t of 3.6 into this, negative 9.8, alpha t plus alpha v sine theta, sine 0. And no, we get a this is negative 35.4. But let's do the same thing and throw it into this one. Alpha v is just cosine 0, and we get 304. So now we'll have a velocity component So our velocity at that point is going to have a component in the x direction of 304 and a component in the y direction of negative 35. So there you go. So we basically have 35 that way and 304 that way. And our slope of this line is negative rise and then run. So we're going to have that divided by that. And hell yeah, we get that same slope. And my m is a little bit different because we took a snippet, you know what I mean? We took a change in time where the slope at that point is the velocity is the component. So if this is vy and this is vx, then that gives us that's the components in the x and the y direction. And that sets up the angle. And the angle there is the same angle there. Okay, so now we know fundamentally that the slope is going to be cool. So we can actually do an equation because this is Vx and this is Vy. And then so tangent of our angle is Vx divided by Vy. So our angle is going to be inverse tangent of Vx divided by Vy. And so if we just do Vx divided by Vy right now, we're going to have V initial cosine theta t, and then Vy is negative 4.9 t squared plus V initial sine theta t plus h. Oh, I was thinking if we divided these we could simplify it, but hell no. Yeah, you can't even factor out a t. Okay, but there's our equation. So we jam that into there, and that gives us our angle for any piece of metal. Now the only thing that you have to jam in here though is your angle and your time. So we have theta and t. And those are going to be dependent on how we set this up. We set it up with theta is equal to 0, and then we got that time 3. So now let's set it up with theta. So I'm going to save that to the side. And maybe this is kind of a good way to do it. Just grab these little sheets of paper and instead of moving on to another sheet of paper, because then we can reference this pretty easily. I'm just trying to find different ways. I don't mind writing small as long as I talk my way through it, and then so you can follow along too. So we're going to choose theta is equal to 45, and if we do that, then we have the y equation. When y is 0, we need to find that. So we're gonna when y is equal to 0, we're gonna find t. Okay, hell yeah. So and then we have this so yeah, we're gonna so y is equal to 0 is equal to negative 4.9 t squared plus v initial sine theta t plus h. And so and then we have all that into our calculator. We have h is that 64 meters. We have v initial is 304 stored as v, and we're going to do theta of 45. And so now if we do that, then we solve. How the hell did we solve for how did we solve for t when theta was 0? Yeah, that was interesting. When theta was 0, this was 0. But now we are just going to have to use, let's do this. I'm so bad at using the quadratic equation. Negative b plus or minus the square root of b squared minus 4ac all divided by 2a. I at least can memorize it. And then we're going to say a is negative 4.9, b is v initial sine theta, and c is h. And so alpha h, cool. Okay, so we're going to go negative 4.9 stored as alpha A, alpha V sine 45 stored as alpha B, and then we have alpha H stored as alpha C. So now we can just plug this in. Negative alpha B plus the square root. We've got to do all divided by. So we're going to do a big parentheses at the beginning. Alpha B squared minus 4 alpha A. Whew. Alpha A, alpha C. Alright, so we got that. Parentheses divided by 2. See, and if I just do divided by 2a, I get the wrong answer. You know what I mean? You have to do parentheses, or you got to divide by 2, divide by a in your calculator. And I like that. I like to use less parentheses and get used to that. Okay, so that's one answer for time. And then, obviously, that was the wrong one. Negative root says this is going to take 44 seconds. You know what I mean? So, and then just to check on reality, what the hell, man? How is this 3.6 seconds? Did we mess up there? I feel like maybe we did. I mean, obviously we got the right slope at 3.6 seconds. I just don't know if 3.6 seconds is when that was going to hit the ground, when this just gave me a value of 44. So we're going to store that as alpha r, and we're going to plug it in. Negative 4.9 alpha r squared plus alpha v sine 45 plus alpha h. And hell no, we don't get the right answer. So that was definitely not 0. Oh, no, it is. We forgot an alpha, another alpha r. Yeah, in the 10 to the negative 1, that's the same thing as 0, so we're good there. But how about the other one? You know what I mean? When alpha v sine theta was horizontal, so when this component was 0, you would have just had 0 for b. So we're going to go 0 stored as alpha b, and then bring up that quadratic. Yes, 3.6 seconds. So that's really bizarre to me. How, like, yes, we understand this projectile is going hella fast, but if you that's so funny, because the velocity this way doesn't help at all. So I get it now. If you have a horizontal velocity this way, it's literally just like dropping a rock from 64 meters up. You know what I mean? And if we do that, the equation for that would be it would have 0 velocity. It would just be negative 4.9 t squared. Because if you had 0 velocity in the y, your change in y would just be negative 9.8. So it'd be negative 4.9 t squared plus h. Yeah, and then that's what we found. So it's just like dropping something. So that's so funny, the fact that when this blows up at 1,000 feet per second, 700 miles per hour, now, so that's the other thing. What's our max time? Because if this blows straight up into the air, we can say our max time is sine 90, which is 1. So we can say alpha v stored as alpha b, so we got that, and then with our initial height. So then we can just rally it out, and we get a time of 62 seconds. So we we won't do that one, as a check on reality, because that's just a particle that goes up and down. But we will use this 44. It's stored as alpha r, so our time is stored as alpha r for theta is equal to 45. And now we can just kind of move on. And now, do we have enough to find the slope? Already, that's all we needed to figure out. We just, for the angle that we chose, we needed to find the time when it impacted the ground. And if we find that time, we can come back to here and find the slope. And we're going to do this in 2 different ways just to double check it, you know what I mean? So we're going to go alpha v cosine 45, alpha r is our time. I'm going to store that as alpha j. Now we're going to do this one. Negative 4.9 alpha r squared plus alpha v sine 45 alpha r plus alpha h. And I'm going to, oh, what the hell? Like that's 0. Oh, my bad. I put in the wrong equation. You know what I mean? You probably caught that a long time ago. This is the position y equation. This has to be velocity y. So velocity y is negative 9.8 t plus v initial sine theta. That's what I'm hoping, is that, you know, I go at such a snail pace, and I'll get better at not getting rushed, because there's no reason. I mean, if you're in it for the long game, well, let's do this. But I do make a ton of mistakes, you know what I mean? And I ain't going watching my videos a bunch and then telling you where all those mistakes are. So I think my videos are thorough enough. When you see a mistake, you might be able to catch it faster than I do. Okay, negative 9.8 alpha r plus alpha v sine 45. Cool. So now this is our value. I'm going to store this as alpha k. So we got alpha j, alpha k. So we're going to do alpha j divided by alpha k. And then we're going to take the inverse tangent of that. Inverse tangent of that answer. So now we have a slope of negative 88.668. And what does that tell us? Well, a slope of 0 is this, and that would be the minimum angle. You know what I mean? So if our slope is pretty steep, so it's rise over run, so it's negative 88 over a slope of like 1. So there you go. And we at 0 degrees, we came up with a slope alpha m of 0.11. So that's fascinating, that if you shoot something horizontal, hell yeah, it got way the crap out here before it hit the ground. But now if you do a 45, it goes up high enough that when it comes down, it's literally, you know, kind of vertical. It has a pretty darn steep slope. And just the time frame on it, just the fact that if you shoot this thing horizontal, it comes down in 3.6 seconds. But if you lob it at a 45, or I mean, it's not lobbed, it's going to 700 miles an hour. It basically goes really, really high and then comes down. This is interesting. You know what I mean? By symmetry, if it went up at a 45, it already is at a 45 right here, and it's only going to get steeper. Oh, perfect. So now I think we actually have our first check on reality, where at any angle that you shoot above the horizontal, the second it comes down past the horizontal again, you're already at a lower angle. So now the question is, I'm curious about 5 degrees from horizontal and negative 5, because the particles that are below horizontal, I just considered them, I ruled them out for whatever reason, but they might actually make a shallower angle. All right, so with that time frame, we're going to do that time frame of r. You know, at 45 degrees, we got a time of alpha r in our calculator. Alpha r was 44.3 seconds. And what we're going to do is we're going to take the x and y at 44.1 second, just before that. So we're going to go 44.1, stored as alpha q, and then we're going to get the position y and x. So we're going to go back to our x position. We can do that one, alpha v, cosine 45, and then alpha q. This is the time right before that. We're going to store that as alpha. Sorry, store that as alpha x. Damn it. Store that as x. Cool. So now we can find the y value. It's going to be negative 4.9 alpha q squared plus alpha v sine 45 alpha r plus alpha h. And this is going to store it as alpha, we'll just store it as alpha y now. And then our alpha t, what was our alpha t for this one? Wasn't it just alpha r? So yeah, so we can find the y value for alpha r. We're going to go just pull this one up. Oh, I'm messing up. Anyway, this has to be alpha q2. So we have 4.9 q squared plus v sine theta alpha q again plus h, and that's going to be my new y value. Nice. And then for my y value at alpha r, sure, then I can come in here and go alpha r, whoops, and then make this alpha r. And oh yeah, that's 0. Holy Toledo, because that's where impact's at 0. So we have that one, but we need to know the x value for that, and it's alpha v cosine 45 alpha r. So that's gonna be our d. So we're gonna have d 0, and then this point is going to be x y. And so we have x and we have y, and now we can find our slope. Our slope is just, we have that y value there. This is going to be d minus x. So we have alpha d minus x. I'm going to just store that as alpha e. So now we're going to have our angle. Angle is inverse tangent of y divided by e. Inverse tangent alpha y divided by alpha e. And we get 45.26 degrees. And no way. So why did we mess up when we took those components for the velocity? Did we just do them wrong? You know what I mean? Because we were saying our velocity at impact, we have an x component and then we have a y component, and then our angle is the same angle there, and then so our inverse tangent is going to be this is vy vx. So we're going to have inverse tangent of vy vx. Did I just get them mixed around? Because now when we go for vy, we got negative 9.8 alpha r plus alpha v sine 45 divided by this alpha v cosine 45. Yeah, so I probably totally messed it up. Yeah, now we have inverse, because I probably took this as my x, my velocity x. I think I made that mistake. You can double check me. But inverse tangent of that answer. No, I'm still not getting a check on reality. But this is good. You know what I mean? This is how you can dial it in and then make sure you're not making mistakes. Because even right here, I'm not linking the two things together. There's two ways to find this slope. One was to figure out at a 45-degree angle what's the time, and I'm pretty confident about that time. And then we said the slope was just going to be the y component, which is the velocity in the y divided by the velocity in the x. We can do this one more time. Negative 9.8 alpha r plus alpha v sine 45 divided by alpha v cosine 45. And then we have inverse tangent of that. And sweet, so we get negative 45.38, and that was very close to that. So so I'm just making tiny little errors on this. So what we'll do is we will let's hash out that equation, because I totally wrote it wrong right here. This was wrong. So our slope, so we already know our slope is going to be or no, the angle, I'm sorry. The angle, and hopefully it's angle min. We're trying to find angle min, is going to be the inverse tangent of the velocity y component, which is negative 9.8. Holy Toledo. So maybe we can simplify. You know what I mean? The fact that I totally butchered this, and did I even get it wrong? You know what I mean? I said this was the x divided by the y, but that's not true. You know what I mean? We come here. Here's our velocity. Here's our components in the x and the components in the y. And then so if we say, what's this angle? Well, tangent of that angle, we already spent 10 minutes about 2 hours ago going over this, is the sine component, vy divided by vx. So we should for sure be able to simplify this. So now we have negative 9.8 t plus v initial sine theta divided by the velocity in the x, which is just v initial cosine theta. Now, we really can't simplify it, but at least that's fairly simple. Yeah, you could combine these two terms and get a tangent theta, but you would still have 1 divided by cosine theta in that term. So I'm totally fine with this term being right here. You know what I mean? The missing link is like, how do you get an equation that finds this minimum? How do you get an equation for theta minimum based on all these? And I think the way, so yeah, I'm still not there yet. We're just still plugging and chugging, you know, just different examples in. And so sweet. So there's my slope equation. And so now that was a hella slope. So now we're going to go theta is equal to 5 degrees, and then we'll go theta is equal to negative 5. So, you know, just throwing in these, like, I mean, you have an equation. If I can't use the equation 4 times without messing up, then even if I have a fundamental understanding of the equation, like, the use of an equation is almost more important than just getting the equation. Okay, so at theta is equal to 5 degrees for our initial, we're going to use this you know, y, when it splats on the ground, that's going to be 0 is equal to negative 4.9 t squared plus v initial sine theta, which is 5 degrees, t plus h. And now we can solve for t. So this is the bummer, just because every time I need to find the time, I need to solve for t using like a quadratic approach. And then once I find that time, then I can shove it back into here, that time and that angle, to find theta minimum. And even for this problem, you know what I mean? Like, I don't care if you know, tonight, if I can't find that perfect equation that links these two together and that minimizes... that minimizes, you know, our angle, you know. So we're just throwing in and getting answers out. So the other way to do this is, you know, it graphically negative 4.9, and this is probably the way to not make errors. In my calculator, this t becomes an x variable, and this y is what 0 is. So we have negative 4.9 x squared plus alpha v sine 5 degrees x plus alpha h. And now we're just going to go zoom. Well, we got to go, I would just graph it and see where it, yeah, perfect. And let's find the 0 and left. All right, we're back. And yeah, we're gonna see where we're at. Holy Toledo! So I just go value 0. Sorry. So I'm just gonna go value 0. So now we're right there, and then find the 0. We're gonna go left bound, right bound, and that's gonna store it. So for this, our time is 7.22 seconds. That's stored as x, and I'm gonna go x stored as alpha p. You know what I mean? So, so our time is alpha p, and that's going to be 7.2 seconds. So now what we do is then we throw that into here. So now we're gonna, and here, you know, I can also, yeah, I mean, could I just throw this in as equation? I need to get better at kind of doing things that make more sense. So, and then we're going to go alpha p plus alpha v sine 5 divided by alpha v cosine 5, and then we're just going to graph that. And it seems like that. Oh, whoa. Did we do the inverse tangent of it? Oh yeah, it's going to give us, sorry, holy Toledo. Did we not set this up right? So we said that we wanted the angle. So how did we not? Is it giving this? Is it giving us the angle from here? So because if we're saying, oh man, this is such a bummer. So right here, this is the velocity in the y, this is the velocity in the x. We're saying that tangent theta is vy vx, and we're saying that the angle should be inverse tangent of vy vx. So now, why didn't that work out? So let's come out over here, and we have alpha v cosine 5. So we have that, and then we have alpha v sine 5, and then we have negative 9.8 plus alpha p, okay, plus that. So we should get a positive divided by alpha v cosine 5. You know what I mean? And then inverse tangent of that is an angle of 4.5. So, and maybe that's what we did, just trace. No, so we messed. So that's just interesting. When we type in something different, we have inverse tangent. We do have a parentheses there. Negative 9.8p plus v sine 5. So we're good there. And then divide it by. And I don't have too many parentheses, right? I have a parentheses here, and then there, and then one final. So we have v cosine 5. And then that red, I mean, that should just chisel out a constant. So we're going to trace that, and we get a constant at negative 8.29. But if we come in and do this, inverse tangent, negative 9.8 alpha p plus alpha v sine 5 divided by alpha v cosine 5. Holy hell. So let's see. So our vy is negative 9.8t plus v initial sine theta. And we got negative 9.8 alpha p. Oh yeah, it's 70. Oh, this is bumming me out. And then inverse tangent of a negative number, so negative 0.2, is going to be a negative angle. Okay, so maybe I'm okay, because it just shows that I'm taking the angle right here, and that's going to be a negative. I mean, if this is negative, it means it's that way. So it technically, oh man, or I guess it's saying from, yeah, these tangents are pretty good, because you're saying, hey, this is theta 0, and then you're saying you're getting a negative angle of that. Because if we use this equation, and then we throw in alpha q, and what was alpha q? Was that 45? I kind of forget. And then graph that. And then we need to actually make our window bigger. Window y max. Oh, 90. It should work out. Well, we'll see if it actually throws a line in there. Yeah, there we go. And so hopefully this is negative 45. It looks, yeah, if that's 90 to negative 90, so we're just going to trace, whoops, just trace one of these. Yeah, so you get negative 45.1. Okay, so we do have a way to do the equation, and we just got an equation. We got an answer of negative 8 degrees. Oh, so right here we got an angle of 6.5. I'm kind of losing it where I don't even remember what that was. Was that a 0 degree angle? I'm sure it was, because now we said if we went at a 5-degree angle, and then by what we said, if we start at any angle up, that means we're going to start with a downward angle, plus we have to finish with, so we're definitely going to start with a steeper. So now we're going to go the other direction, and I'm going to throw in oh, sorry, we should throw in alpha p and actually store that value. But I'm satisfied with tonight, because at no point am I making huge errors. At no point am I making like major mistakes, or if I do make the mistakes where I'm just like, oh shoot, something's not adding up, I can get back on track. And I think that's really important for problems. So what the hell happened here? Negative 9.8. So where's our equation? Negative 9.8 p plus v sine 5, and then 0.5. So cool. So we're gonna at a 5-degree angle, we're gonna have an impact angle, and I'm gonna trace this out. And okay, so we're gonna have alpha y of negative 8. And when you trace, you know, it'll store these values for x and y. So we quit, and then we'll go alpha y, and there you go. It stores that. So now I'm gonna store that is alpha z. So we have alpha theta as 6.5. I think that's when we did a 0-degree launch. So this is 0 degrees. Now I have alpha at 5 degrees, and I have an 8.3 degree angle. So now we're going to do. So now we have the process down. You know, we do these two things. So now my next angle is negative 5 degrees. And we're going to go back to this equation and go negative 5, negative 5. Just right now I'm going to switch this to negative 5, even though we don't have the right time in there. And then I guess I'll just graph that. I have to wait for the other one to compute, but you know what I mean, that's okay. I'm going to go trace, trace. Oh, it already was, so 0, and then I'm going to go 0 left bound, right bound, capture that 0. So that's our new time. So I'm going to store x. That's our new time stored as alpha O. So at 0, at negative 5 degrees, our time is alpha O of 1.8 seconds. And now we can throw alpha O into this equation, alpha O. And that's it. And then graph it. I guess what a waste of time to actually wait this 10 seconds for that to graph. Alright, so that graphed, and we're going to trace it. And now we have negative 8.29. You know what I mean? So now we're going to quit. We're going to bring up alpha y. Store that is, what should we store it? Well, what was the other one? Oh, it was alpha z. So we're going to bring up alpha z. Yeah, that's the same. So why is it? And maybe there's a place where it's going to be the same. At negative. Oh, this is fascinating. So we just proved that at negative 5 degrees it's going to be the same at positive 5 degrees. And so that must mean at 45 degrees that would be interesting. So if that's the case. So I think, like right now, I'm feeling pretty confident that the lowest angle is the sparks that go totally horizontal. And from the axiom that if it goes above the horizon and then comes back down the horizon, it already has some sort of angle that's worse than angle minimum of 0. And then that angle is just going to get increasingly bigger. You're going to have a bigger angle max. Compared to if you just go totally horizontal, it already is at the horizon at 0 degrees, and then when it lands, and then plus you just have so much horizontal velocity, but that is irrelevant to the problem, because when it does land, you'll have the lowest angle, because we just showed that with an angle of negative 5, that didn't help. And because I think I did it right, alpha O and then negative 5, and yeah, we got that same value. Cool. And we know by definition making the angle steeper makes it worse. And so let's just do another angle of -10. And then we probably will call it. So we're going to come up here. We're going to go -10. I might as well switch these to -10 just so I'm on track and I don't forget about that later. Graph it. We're going to get the 0 for the time, and that time I'm going to store as alpha n. I'm going to trace 0, value 0, left bound, whoops, left, oh, damn it. Left bound, right bound, and then the guess, 1 point. Okay, so we got that. So we got x stored as alpha n, and this is going to be 1.09. And now we're going to throw it into this equation, alpha n. So we just have one thing to maneuver here. Obviously, if you do this in Excel, it'll be easier. But there's something staring at an Excel screen that I don't know. It doesn't help my learning process. It's just nice to have a calculator and some pen and paper. And then if I have to do some scenarios, I don't mind doing those scenarios. So hopefully I wrote that in correct. And we can trace this, and we get -11. Okay, so I'm going to alpha y stored as alpha, I'm going to store that as alpha w. So now I guess we're going to do +10. And you know, hopefully there is a correlation where +10 gives the same angle as -10. That would be a pretty cool relationship. I'm going to find the 0. Whoops. So trace, and then find the 0. Left bound, right bound, guess. Cool. That's a different time though. You know what I mean? Yeah, isn't it? Well, but we're at a different different angle though. Different angle. So yeah. So we have this x. We're going to store that as alpha L. And this is going to be theta is equal to 10 degrees, and time is alpha L of 11.9. And then so we go back into here, change this to alpha L, graph it. And then, yeah, it'll be cool if we find that relationship. Then that'll give me some confidence that we're on the right track, and there is some symmetry here, which is cool. So we're going to trace. Oh, damn it. Oh, hell no. No. I'm just going to... Oh, I hate this. When the window gets messed up, I have no idea how to get the window like back good. So my y is going to be -90 to 90, and then my x is going to be what? For time, it's going to be -10 to yeah, we only need to do 20. Is that right? Yeah, close enough. Alright, so now we're going to do value of 10. Okay, and then I'm going to go 0, left bound. What the hell am I even doing? I'm just tracing and I'm getting this. And so I get a value of -11.9. And I think that's the same, so I'm going to go alpha y, store that as alpha v, and alpha w is the same. Cool. So we do get symmetry, and so now I'm pretty confident in my answer that the sparks that have the lowest angle are the ones that come out perfectly horizontal. And so that's fascinating, because one part of this problem that I was interested in is like, well, they didn't specify whether this thing was going straight up or straight down. You know what I mean? The velocity in you know, because if you had this cannon that went in an arced path, then which sparks would land the same. And I think it would be the same, the sparks that go this way. You just have a higher velocity. You're basically just adding the velocity of 1,000 plus the velocity in the x direction initial. And those two really don't change the problem. And so that was the one thing that was my question, is just like, do I have to do this problem again if I angle the mortar at some sort of angle so it doesn't arc and then blows up right at the top of its trajectory? And I would say then no for that. This problem does change if this thing goes up and then starts to come down and then blows up. I think that does change things, because now you have a velocity component down, and then so the sparks that are going this way, so the spark that is going this way also has a velocity component down. So then I would say that I'm fairly confident that whatever that velocity component down is, you would bring that velocity component right here, and it would be whatever whatever angle, because here's your 1,000. And then let's say you have a downward velocity of 50. Well, you would take that 50 and 1,000, and then whatever angle that would be, that is going to be your angle for minimum. Because if you just take the horizontal, it already has a horizontal of 1,000, but then a downward component. So it is like shooting it straight down. Where if you take that downward velocity of the mortar when it explodes, and you do an upward angle that makes those sparks, it's like theoretically those sparks are going horizontal, because when they blow up this way, or that angle, they cancel out the velocity downward. Okay, so hell yeah. And that's what we're doing. That's what I'm fascinated in doing in my videos, is like, can I make something make sense to me? And I apologize just for, scratching up the same area a bunch of times. But I like this method. It's like, damn, we just stuck with one page, maybe 2 pages. But this was a good introduction. I won't do this every time because I can just refer to these videos. But anytime I think of a different way to bring up the concept of acceleration as constant and how do we get the equations, and this was the first time taking the equations out of the book, because I always hated these. These equations sucked, you know what I mean? They didn't seem like they had any bearing in reality or how you got them, and I think that's really frustrating. I don't mind the area of a friggin' circle being pi r squared. I get that. But to have an equation that is so nitpicky, you know what I mean? It was like, well, you don't have acceleration in the x, or maybe your position, you don't have a position x. All right, hell yeah. So I think you get that point that I'm trying to make. But this problem, I don't know what to do next, because I've identified that we need a quadratic to figure out the time components. And then once we find the time, then we have to shove it back into this equation to find the angle. And so I'm having a hard time figuring out how to minimize that. Let me go back to this equation, because we're saying the slope is the velocity the velocity final has a y component. This is velocity y final, and it has a velocity x final component. Hey, look at me. I'm actually using the equations. Velocity x final and velocity y final. Those are the 2 equations, and we're going to and we can obviously find the angle. We can also find the positive number of the angle just by making this negative as well. Which that was part of the problem, where it's just like at some point something's going to be negative. You know what I mean? We have to create an origin. Our velocity is going to be negative, but we just know that this angle can be now this equation with that negative in there, and we can get a positive angle. Okay, so I'm still scratching my head, because even if we use t is equal to b squared, t, using the quadratic, t is equal to negative b plus or minus the square root of b squared minus 4ac over 2a, and we know that we need the negative root or whatever for all angles. I guess I would have to prove that, because even the other day, just by changing just something small, it would the positive root was the one you needed for time, or the negative root was the one, so there was no consistency on that. But I think if you use the same equation, I'm just guessing there's consistency on the quadratic, where you just be like, hell yeah, we're taking the negative root, so this is just a number, so then you could take that and put it in here, and this is a number that's a function of, it's going to be a function of acceleration, the theta, the velocity initial, and the height, so we have a function of acceleration, velocity initial, theta, and then the height. And the t variable is what we want. So then when you throw it back into here, it's all the same. We have acceleration, velocity, theta, and height. And we're just saying acceleration is given, velocity initial is given, and height is given. And what we want to find is... yeah, because they're saying height is given, and then that velocity is given, and obviously acceleration is given since we're on the Earth. We're not taking these fireworks to the moon. I don't think they'd light up on the moon. So you would have an equation that would just be a function of the initial initial. So, I would call this your angle guess. Your guesstimate of where the sparks are. And what you're trying to find is the fact that this is the lowest. But cool, we found this final equation to get the angle, but I don't think this is where you go to actually maximize or minimize this value. So if we do have this angle tangent, let's say angle tangent is 0.1. Okay, that's a low angle. Angle tangent is 0.2. That's a higher angle. Angle tangent is 0.0001. That's going to be a low angle. Cool. So now we know that just this in here, if this is small, then we know when we're minimizing this. Okay, hell yeah. So now I think we got it. So now we have just these two parameters are velocity y divided by velocity x. And they basically tell you with the inverse tangent the angle. But when this is low, you have minimized the angle. That is proportional. When this is small and this is big. So now what we can do is we can, and if this ever approached a minimum, like it's not going to approach 0. The angle won't be 0. So I just don't know how you're finding, like if your minimum is a slope of 0, cool. But we're not finding a slope of 0. We're just finding the minimum. So I don't know, but I'm going to write that out and see if it helps me. So we got negative 9.8 t plus v initial sine theta divided by, I'm going to do the negative v initial cosine theta, because now that makes this a positive quantity. And I could also rearrange it to just be 9.8 t minus v initial sine theta. Well, how do I factor through a negative 1 right here? So if I factor through a negative 1, now I'm going to get 9.8 minus v initial. Yeah, I was on the right track. And now we just have v initial cosine theta. Hopefully I didn't make an error there. And this is going to be equal. So this is our angle naught, our angle of our sparks. And this is our angle final. And so yeah, so we have an equation for angle final based on the initial angle. So let's just, I need to do more just graphing things, you know, and just mentally. So if here is angle, well, this is your y term and this is your x term. So our angle initial is going to be 0 to, let's say, 90. And then our angle final, because our angle final is going to be, so at 0 we do have a minimum. Oh hell yeah, I didn't realize it. But if we look at the graph this way, when we throw in an initial angle of 0, our angle final is so this is angle final and this is angle initial. So yeah, just even doing I need to do more of this. I already said that once, but just, you know, make a graph and then just throw some numbers at it. I mean, even just mentally. So oh, it's so hard though. So when we're 0 degrees here, we're going to have the smallest angle. Angle final is going to be hella small. When we're at 45, holy Toledo, our angle was already 45. We were basically right there. And then everything in between. And then we said if we went to a negative angle, because this angle initial could be negative. We agreed with that. We could have a negative. And obviously we could be going the other direction too. But we're just going to stick with half the problem being a positive initial angle to real steep to be 90. Obviously that creates a 90-degree angle. That's the worst. Or a straight down angle. That's the worst. So we can have a negative 90 or a positive 90. We can have a negative 45 or a positive 45. And we analyzed a 0, we analyzed a positive 5, we analyzed a negative 5. Both the positive 5 and the negative 5 created the same angle at the bottom. Hell yeah. So at 5 degrees and negative 5 degrees, we caught the same angle, but it wasn't minimum. The angle minimum was at 0. And so we get an equation for this. So sweet. So this is the equation for theta final. Yeah. So then to find the minimum, it's where this slope is the smallest. So hell yeah. And I like using these cards, because half of doing this is just for me to figure out and for you to see how things get figured out. Because I actually am doing better at figuring things out with talking into the camera than just, you know, scratching my head. Yeah. All right, hell yeah. And this is my favorite part, because I'm learning how differentiation works. And it's just like, for the life of me, I don't know how people can learn differential calculus and just think, oh, hell yeah, I got this. Like, I think, you know, it's the slope. You know what I mean? So I guess I just almost need to do more just algebra, you know, 2 equations, where you're just like, hey, let's find the slope. Always trying to find the slope. I get the area under the curve. I feel like that makes sense, because we started with acceleration. Area under that curve is velocity. Area under that curve of that equation is position. But now, you know, anytime you're trying to find, but you know, the question is so fascinating. Hey, we have an equation for the angle final. How do you minimize this angle? Well, you use differentiation. You say, hey, the change in angle final divided by the change in angle initial. You know what I mean? This is the same thing as saying dy dx. This is our y side and this is our x side. You know, that's our x variable. And so what we're saying is that when this is at a, and I shouldn't say something, I mean, because obviously the graph could look like that. You know what I mean? So you have to, and when the slope is 0, it could be a maximum. You know what I mean? So just doing dy dx is equal to 0 isn't enough to be like, oh hell yeah, that's the minimum. It could be the max or it could be the minimum. You know what I mean? Because if we threw a couple points at this and we saw a relationship with our graph that went this way, well, we would know that that's the max. And if we were trying to find the minimum, well, maybe this problem only has some ceilings where here's the ground, and you know what I mean. theta final is, I think you get what I'm saying. You know what I mean? Hey, this is theta this is theta initial, this is theta final, and this is our origin 0, 0, and maybe anyway, and maybe that's the value of theta final that's the lowest in your graph. I'm just picking out a point from my head that, you know, having parameters on the problem, just because you have an equation that can stretch from negative infinity to infinity, is just like, well, go back to your problem, and you know, even for this, the angle is going to materialize when it hits the ground. But yeah, that's taken care of with our equations. Oh, okay. So, but again, we have this time function in here. So I guess I'm not 100% enthusiastic right now, because if we differentiate, if we do the common differentiation of d theta or dy dx, and we differentiate with respect to x, we do have that time component. But is it just all right to leave that alone? You know what I mean? Is that just a constant? Or I think this time component is a function of the initial angle. You know what I mean? So I don't. So I'm not excited to see if I could actually get the right answer on this one. But anyway, let's keep at it. So what we do is we have a derivative, and then so here's angle final as a function of, you know, angle initial, and then that's what we have. We have angle final as a function of angle initial, but it's also a function of time, which is a bummer, and we're just differentiating with respect to angle initial. So that's a bummer, because we also have that in there. Anyway, well, I guess let's write it in. So we have 9.8 t minus v initial sine theta divided by v initial cosine theta initial. And that's our function of theta, and we're going to do d theta initial. So now we would just use common rules of differentiation, but we do have this time thing here, and that's going to be a function of the quadratic equation. Now there's definitely plenty of times in math where you're just like, well, just because I'm on the right track and I have something that could work does not mean that this is the simplest way to get there, or even a good way to get there. I was scratching my head for the life of me if there was any way to get rid of this h. You know what I mean? To have the origin start at, you know, 0. When y is equal to 0, the origin is 0. But then that would mean when we solve for t, we have to throw in the h over here of negative h. So that does not help. Oh, man. And but maybe there's just some pro-relationship that you can go back to this 9.8 t minus v initial sine theta divided by v initial cosine theta. And then let's separate this, just because I might want to at some point anyway. So we have v initial cosine theta minus, and this is just going to be tangent theta. Cool. So because the v initials cancel and you have sine divided by cosine. And now this is what you would be trying to minimize. You're trying to minimize this equation. But damn it, we have two variables here. But is that all right? Couldn't we? What are we trying to do with this? We're just trying to minimize it. You know what I mean? Are you going to set this equal to 0? Does that minimize it? Yeah, no duh. Holy Toledo. Okay, my bad, my bad. Yeah, because even, I don't know what the hell I was thinking. I got off on a tangent of doing that max. But obviously, yeah, the slope at that point is 0, so you can set this equal to 0. That's the whole point of finding minimums and max. Because once you set that equal to 0, yeah, things can fall out. So in essence, we're just setting this to 0. So let's do it. 9.8 t is equal to, divided by v initial cosine theta is equal to tangent theta. And now we're going to have 9.8 t. Let's turn this tangent theta back into sine theta cosine theta. And now we're going to bring up the v initial cosine theta. Cosine thetas cancel. And now we have 9.8 t is equal to v initial sine theta. So now we have a relationship between time is equal to v initial sine theta divided by 9.8. I feel like I'm doing nothing right now, but we could also do the other thing and go 9.8 t is equal to v initial, 9.8 t divided by v initial, and then inverse sine of that is theta. So theta is equal to inverse sine of 9.8 t divided by v initial. And yeah, let's just throw that in just as an equation. So we're going to go inverse sine 9.8. Was alpha r, let's see, alpha r, no, was it alpha q, alpha p, alpha s, alpha t? Yeah, what was the one at 0? At 0 degrees, did we get 3.6? Is that alpha t? So we're going to go inverse sine of 9.8 alpha t divided by alpha v. Nope, that sucked. 9.8 alpha t divided by alpha v. But let's do the absolute value minus answer and then inverse tangent of that. Nope, I don't know what I'm doing at this point now. So, bummer. I mean, obviously we got the relationship. I'm just trying to find if there's a way to actually. So what the hell does it say? Find the smallest angle that the. All right, this problem just said find the smallest angle that the final velocity of an impacting fragment makes with the horizon. We already found that, and it was theta of 6.5 degrees. You know what I mean? So we found that 6.5 degrees just by guessing. But now, I mean, I'm trying to find it from a purely mathematical approach that says the angle final, or the angle minimum, is going to be the inverse tangent of Vy Vx. And so, yeah, let's just throw this stuff in here, and then we're going to say d final d theta initial. When that's equal to 0, that is going to give us an equation, you know what I mean, blah blah blah, with theta initial in it. Once we differentiate, so we're going to differentiate that, get that equation, and then when that, that equation equal to 0, when we solve for that theta initial, that's going to be the theta initial that is going to be our theta minimum. And I think we can do it. Probably can't do it. So we have negative 9.8 t. I'm going to give it one shot though. You know what I mean? And then we have Vx, V initial cosine theta. So that is what's getting inverse tangented. And we need to get an equation for t. So t is negative b plus or minus the square root of b squared minus 4ac divided by 2a. where B is, so yes, it's this equation that you're trying to solve. So B is V initial sine theta. A is negative 4.9. That won't change. That's just acceleration. If you want to say it's G divided by 2, cool. And then C is the height. I mean, I guess I'm trying to solve the problem that would be like the 3-star problem. Is like derive an equation for height and velocity. So you can input height and velocity into an equation, and then what's your output is going to be your theta minimum. You know what I mean? That's what we're trying to find. And I think we can do it. The only thing that we need to do is figure out whether it's the positive root or the negative root. So let's just go back to an angle. I'm just going to do an angle of 0. And that's going to give us... we'll do an angle of 0 degrees, and an angle of 5 to confirm what's the negative and positive root. So our equation for y is negative 4.9 t squared plus v initial sine theta t plus h. So here's our a, there's our b, there's our c. So we're going to go negative 4.9 stored as alpha a. We're going to go alpha v sine 0 stored as alpha b, that's just 0, and then we're going to do a height, alpha h, stored as alpha c. And now we're going to run the quadratic. And I don't think I have it saved, but we'll see. I don't mind scrolling up for a whole minute just to not write the quadratic equation. There's nothing that I despise more than the quadratic equation, just because there's so many places for errors. Alpha b squared minus 4ac. And there's so many places for just a misunderstanding of what the hell's actually going on. Alright, we need a parentheses in the beginning. Parentheses at the end, divided by 2a. I guess that wasn't so hard, but we even messed up. We didn't divide by 2a. We didn't divide by 2a. We divided by 2 and then multiplied by a. Okay, hell yeah. So the positive root wasn't the good one. Negative root was the good one, and that's alpha t. So now we're going to do theta of 5. And so we're going to go alpha v sine 5 stored as alpha b. And is it the negative root? Hell yeah. And now we're going to go alpha v sine negative 5 stored as alpha b. And now we're going to see if the negative root works. Hell yeah. So it's the negative root the entire time. That's what I thought. Negative root will work. So now we need to kind of simplify this. So we have t is equal to v initial sine theta minus the square root of v initial squared sine theta squared, that's that b squared, minus negative 4.9. This is where you can get confused, because it's minus 4, oh bummer, minus 4 times negative 4.9, because this a is negative 4.9, you know what I mean? So you have two negatives there, and then c is h. Cool. Yeah, that's it, because there's no b term in there. Alright, hell yeah. And right now I'm just going to get the hell rid of that negative. Cool. And then we're going to go all divided by 2 times negative 9, negative 4.9. Negative 4.9. Okay, sweet. Oh, this thing's ugly. So this term is going to go to a negative 9.8. This term is going to go to a 4 times 4.9. Alright, hell yeah, home stretch. So I took a little break, and it actually took quite a bit of a break, a couple hours. And I spent just a little bit of time going from, so we have this theta final, and we want to do change in theta final divided by change in theta initial, and we want to figure out when that's 0. We know it's going to have a minimum, and we know that inside the bracket, as long as that's at a minimum, then we should be good to go. But no, I think I'm just going to throw it into the computer. You know what I mean? Go to like Wolfram Alpha. But I was interested in figuring out just the whole process of this, because you have this function as a function of time. So then we have to take that original y, negative 4.9 t squared plus v initial sine theta t plus h. And then we need to set the y is equal to 0 because that's when it's going to impact the ground. And that's going to be the time it takes to do that. And so that's when we use Pythagorean's theorem. Now what I did, I'm just going to go over this. But this is... I don't like this form of, I'm sorry, I said Pythagorean's theorem. No, the quadratic equation to solve for t, since we have a quadratic formula here. I don't like the quadratic formula. I like to derive it from scratch. So we go ax squared plus bx is equal to c. We have to divide everything by a just to get x squared, by itself. That makes sense. So we go b over a, and then the c over a part goes instantly to the other side, so we've only done that so far. But then now we get to here, we need like x plus something, and this term is always going to be half the middle term, because then when you do x times b 2a and then b 2a times x, those two terms are going to add to that. But then when you do this and you do this squared, you're going to get a b squared divided by 2a squared term. And so you have to add that to both sides of the equation. So that's what we do here. Then you have finally you got your x plus b over 2a squared, so you can take the square root of it. That's when this square root pops in, plus or minus the square root. And then all you're left with is just x plus b divided by 2a. So you're just going to subtract the negative b over 2a. So now we have literally our function of x is just that. And then so I noticed that a is equal to g divided by 2, in our equation. That's that negative 4.9. And then b is going to be v initial sine theta. So we got that. And then c is just h. So we go negative h, but then we got a is g divided by 2. So we got negative 2 2hg, so we got to there, and then plus v initial sine theta, it's just that b term squared, divided by 2a squared is going to be, well, I just want to know what the hell, it's going to be 2 squared, it's going to be 2 squared a squared. So this is a, g divided by 2, so that's going to be g squared divided by 4, and then we're going to multiply it by 2 squared, which is 4. So the 4's cancel, and this term you're just left with g squared. Cool. And then this is vi sine theta, cool, divided by 2a. Well, a is g divided by 2, so that's just going to be g. And then you didn't have this g squared, but I want to multiply by a g divided by g. That's going to be a unit of 1. So it doesn't change this value, but now I can see that these two are g's, so then I can actually combine this whole thing, and then we just have that. Which is the same thing as saying taking the square root of that, square root of that. Cool. Well, now this just pops out of the equation, and then what we're left with is that square root upstairs. And then I just rearranged v squared sine theta squared minus 2hg divided by g. And then once we get to here, is there anything else we can do? Oh yeah, so hell yeah. So once you get to here, this is now our x, which is our t. You know what I mean? And so what the hell were we trying to shove it in? Well, we were trying to shove it into there. So now we're trying to actually shove it into this equation, at least right there. This is gt. So now we're going to multiply everything here by g. Well, the g's cancel, and then but if we actually do shove it in, Then we get the g's cancel, and then we have a minus v sine theta. Hey, look, we have a plus v sine theta. So those cancel. And so it's pretty sweet. Like we're getting pretty far. Now we have the square root of v initial squared sine theta squared minus 2hg for this part, divided by v initial cosine theta. And that's just going to be the inverse tangent of that. And that's going to be theta final. And if we want to take d theta final with respect to theta, initial, just theta right here, and set that equal to 0, well, first we actually need to figure out what the derivative of this and then set it equal to 0. So I'm just going to take it to the computer at Wolfram Alpha right now, because that's where I got. And well, I'm kind of bummed because I'll actually just have to throw in my initial values of, I'm a v and stuff, and then see if I can figure out how those popped out. So, yep. I guess one way to do is just throw in an initial value of v as 1, and then a height of, I don't know actually how I'm going to, well, yeah, because I can throw in any v and h. So, yeah, so in the computer, let's simplify this. Let's say v initial is 1 and h is 1. You know what I mean? 1 what? Whatever. Meters per second, and then this is meters. And it's going to blow up. We can still, I mean, everything still applies. If we have a projectile that goes up 1 meter, blows up, and then has an initial velocity of 1 meter per second, from the sparks. And it's going to be the same. We'll still have some height here, so hell yeah. So that should work out. So our equation would just be sine squared theta minus 2g divided by divided by cosine theta, and it's the square root of that, and and then you're going to take the inverse tangent of that. So sorry about that. Inverse tangent, sine squared theta minus 2g divided by cosine theta. I think that's the first thing to do, is just see if I can generate a derivative for that in the computer, and then bring it back. Once I get the equation for that derivative, I'm going to set it equal to 0. And then, I guess at the end of the day, I'm going to imagine it's so complicated I can't actually isolate theta as something over here. But I'll just throw it in my calculator and solve for where theta crosses the 0. You know what I mean? This is a y in a function of x, and so where y is equal to 0, where the value of x that makes this 0 is our minimum angle. That's going to be our theta final minimum angle. Apologize. No. That's going to be our theta initial that creates, you know what I mean, d theta final, d theta initial. That, this is equal to the derivative of that. The change in the final angle is 0 compared to the, man, derivatives are so hard to explain just off the cuff. But, okay, hell yeah, I'm going to catch you on the flip side. Alright, hell yeah, so we're back, and so I definitely simplified this even farther. I just said it was sine x squared minus 1 divided by cosine theta. And holy Toledo, the square root's upstairs. I didn't even do the square root, but anyway, I think it's fine because if this, you can see, you still have to do the cosine part downstairs, because if we're trying to take the derivative of it, and where the, oh man, so crazy. But anyway, so where the minimum is 0. You know what I mean? So this says that the slope is 0 right at theta. You know, the trajectory of theta initial is equal to 0 degrees. So man, so that's kind of where I got with this problem, and I think I don't know. It didn't look like something that I wanted to integrate, and the fact that the way we did it with using the quadratic to shove it in, you know, we got something fairly decent, you know, close, that might be oh, and then what did we do? Yeah, so I mean, this is the equation that I should have shoved into Wolfram alpha, but it's going to look the same. You know what I mean? That's why you don't need the constants here. I just forgot to do the square root on top. Oh man, I mean, should I do that? I don't think so. Maybe at the very end of the video, I'll try to throw it in to see what it looks like. But now what we can do is we can go back to the original problem and check it ourselves. So what we're going to do is we're going to throw in a theta of 0.01, and then so that's theta initial, and then do a theta initial of negative 0.01. We could even make it smaller. But what we're going to find is then we're going to find the change in f. I mean, we're going to find the final angle of impact, angle final, with this case, and then we'll find the angle final with this case, and then we can find the change in angle final. So let's say well, the crazy thing is that these will be the same angles, just because we already know that we have a minimum, and so like these two terms are going to be the same. So I apologize. We're gonna go 0.01 and 0 degrees, and we know 0 is going to be. So we'll do this. We're going to go theta is 0 degrees, and then theta is going to be 0.001, and we'll really make it small. And now we're going to see if. But so what we're setting up is the change in theta final divided by the change in theta initial. So we have this part, we've changed theta initial by 0.001 minus 0, the second minus the first. So what we're going to do is find the theta final of 0.001 theta initial minus theta final of 0. And once we do that, then we'll see this number. Hopefully this number is super tiny. This number is 1/1000th of an angle, but hopefully that number's fairly big compared to this number. Hopefully this number is just absolutely tiny. So basically what this will say is that we don't have any change, and this will be a minimum. And we already know it's a minimum. We know it could be a maximum, but we know it's not a maximum. Oh, and then that's fascinating, because that's the other thing to do, is to, how do you know that it's not a maximum? Well, you take the value at, how the hell do you know it's not a maximum? You, my brain can't handle it. But we're gonna do this and then probably be done. So I'm gonna clear out all these. Sure. So now we have negative 4.9 x squared plus v sine, and theta is going to be, we're going to do that 0, and then solve for x. So we're just going to graph that, and we're going to get the 0. So we're going to go left bound, right bound, and then the 0. That's 3.14. And don't we have that stored? Yeah, so we have that stored as t. So the time on this one will be t. And now let's throw in the other one. we're going to go, whoa. We're going to go 0.001. There you go. And then we're going to graph that. Should be really close. So we're going to get a 0 there, left bound, right bound, and cool. And now we're going to take that x and then store that as s. So now we have alpha t, alpha s. Is there a difference? Yeah, there's a small difference. So now this is alpha s for the time. Alright, hell yeah. So, and this, now you don't have to worry about using differential equations. I mean, you're actually understanding what a differential equation is by doing it. And this is considered, I think some of the books, you know, I don't know if it's all called the Euler's method, but yeah, when you're just doing this part, it's such a great method to use. Okay, so now we have that time, and so now we need our equation. You know what I mean? Did we save it? What the hell's our equation for? I mean, it should be here somewhere. All right, hell yeah. Let's rederive that equation. So you know what I mean? Because what we said is that we're going to have a final velocity upon impact. It's going to have a velocity y component and then a velocity x component. So this is the velocity y component. And then our angle is going to be, the angle is equal to the inverse tangent of Vy divided by Vx. Okay, so Vx, no, Vy is on top. So we're going to have inverse tangent of Vy is negative 9.8 t. That's where that t gets in. And V initial sine theta. So our first one's 0, our second one's 0.001. First one's t, and the second one is s. We're going to divide that by Vx, which is V initial cosine theta. First one's 0, second one is 0.001. Okay, and I did erase it from my calculator, but let's do it. So we're going to go inverse tangent of negative 9.8 alpha t plus alpha v sine 0. And I guess I need another parentheses divided by alpha v cosine 0. Oh, I apologize. We don't need to graph it that way. It's so dumb. So negative 9.8 alpha t plus alpha v sine 0 divided by alpha v cosine 0. And cool. So we have, so at theta, shouldn't this angle didn't we mess up? Because didn't we say theta was going to be 6.5 if we had that initial t? Oh, whoa, yeah. Because I did the tangent, so we need to do the inverse tangent. My bad. So I'm glad we caught that. So we have inverse. See how many places you can just make errors? It's crazy. Okay, so now we have the inverse tangent. No, we're still getting the wrong. So Vy is negative 9.8. Alpha t is our time plus v sine theta. Divided by, oh yeah, no, yeah, just v cosine theta. V cosine theta. Alright, so this totally sucks. And then mode is in degrees. So, holy hell. Negative 9.8. We're gonna, what's our alpha t again? Yeah, we're good there. So we have, and are we doing this right? So we have tangent of the angle is Vy divided by Vx. Vy is that part. Vx is that part. It's so fascinating how you can get something once and then, you know, you just don't even know what you're doing wrong. Negative 9.8 t plus v. Maybe my v changed. I don't think so. Oh, hell yeah. Okay. No. My bad. Yeah, perfect. My v changed. You know what I mean? We actually say v as an angle. Holy hell. That's why these calculators need way more variables. And it should, like, hey, you've already used that letter in the last 10 minutes. Okay, so we have to go back and actually, so we had 1,000 feet per second, and we need that in meters per second. So we need to get that 6, what was it, like, but anyway, feet per second to meters per second. So we're going to go 1,000 times 12 times 25.4 divided by 1,000. That's going to be meters per, and then times 3,600. No. 1,000 feet is inches, is times 25.4 is millimeters, divided by 1,000. That's going to be meters per second. Sweet. Stored as alpha v. Holy hell. Okay, and then now we got that value. Alpha theta was 6.53. Man, I don't know why we're off just by a little bit. Alpha v 304.8, so that should be good. Alpha g negative 9.8 stored as alpha g. Yeah, we'll pull it up one more time. Negative 6.62. Yeah, I don't trust it. You know what I mean? Because we thought it was 6.65 and alpha theta was 6.5. That's what we thought we were going to get. And the negative, we just do a negative right there to actually, you know, make it a positive angle. But 6.62 alpha t. So I'm gonna check my alpha t again. Oh, and then because the other thing we can do is the quadratic equation, and I need to use it more. Negative b plus or minus the square root of b squared minus 4ac divided by 2a. So a is g divided by 2, so we're going to go alpha a, perfect. And then alpha b is v initial sine theta. So that's going to be alpha v sine theta. That's just 0 for ours, so we're going to go stored as alpha b. And then alpha c is h, stored as c. So now we can go negative b, and I think it's the minus root, and then alpha b squared minus 4 alpha a alpha c, all divided by 2a. Okay, so that's our time value, and is it? Yeah, it is slightly different. So so my bad getting. I don't think I actually saved it. I think this one was slightly off. But if we're doing an angle of 0, this is the value that we want. We're going to store that as alpha t, and then when we go back and use this equation, well, now we're off just a little bit again. Alpha b is 0, alpha a, alpha c, and then alpha v. Stored as alpha t. Alright, such is life. You know what I mean? This is probably accurate. This is probably going to be, so angle final, I'm going to store that as alpha theta. And so now we're going to throw in, for our b term, it's v initial sine theta, which is alpha v sine 0.001, and then we're going to store that as b. That's the only thing that changes on our quadratic, and we get that as our time, and we're just going to, and see, even this, using the quadratic, it's a little different than the solver. So I'm sure this quadratic equation is better than the solver in the calculator. I can't imagine why the solver in the calculator would have any error in it. But yeah, I mean, that's what we're solving right there. And that's our B term, that's our A term, and that's our H term. Okay, but so I'm just going to pull up that quadratic. So we're going to store that as alpha S, and then we're going to go to our tangent equation, and then throw in 0.001 and 0.001, and then we have our time value as S, alpha S, and then so here's our other angle. So we're going to store that as alpha Z and alpha theta, and we see that alpha Z is a little bit bigger of an angle. Yeah, so yeah. And then we have to go back to our differential, and we see that this is going to be okay, so this is stored in our calculator as Z, and this is stored in our calculator as theta. Alpha Z is bigger than alpha theta. And so we will have a difference there, and then we'll have a difference here of 0.001. So I'm going to do alpha Z minus alpha theta. That difference is 7.5 times 10 to the negative 8. So that's 0.123456707.5. Now we're going to divide that by 0.001. So just visually you see that the change in theta is approximately 0 compared to just a normal change in angle. I know a thousandth of a degree isn't a normal change, but proportionally this is no change. So no change when you, so this is a minimum. So there you go. So that's the minimum value. And I since this video is so long anyway, I'm so bummed that I can't answer my own question. Is like, how do you know it's a minimum? I mean, we found the change. We found the change was really small over a normal change. So we changed the angle by this much, and we saw that the change in the final angle was just potatoes. You know, it was nothing. But we still need to figure out if that was a minimum. So the equation, so let's go back to the equation. The equation says, hey, this is theta initial, and then this is theta final. And what we're seeing is if our graph is right here at 0, 0, when we throw in theta initial of 0, we're getting a minimum. So what we should see is if we throw in theta of 1 degree or negative 1 degree, we will have a higher angle. And we've already done that. We threw in an angle of 5 degrees and negative 5, and we get angles higher. If we got angles lower, well hell yeah, we would have a maximum here, and there obviously would be a lower angle. So in words, that was a pretty good way to explain it. And I swear, I'm going to go do more graphs. Like, anytime you have a relationship between two things, like, friggin' A, just make a graph and then do a really simplistic graph of what it looks like. So, man, you know what I mean? I'm satisfied with this one, but just a little bit brutal because it hit a wall for me of... well, just differential equations that are too crazy. You know, I went to my book, and yeah, we'll end with this, because this is fascinating. Because just even in the book, the differential equations, I was just like, well, where's the differential equation for sine squared x? Well, you don't need it. So I actually kind of learned something here, because you have differentiation by the product rule. You know what I mean? So we have... differentiation. If you're trying to differentiate uv, well, you have to take the first times the derivative. That's what people say. The first times the derivative of the second plus the second times the derivative of the first. So, I mean, that kind of blew my mind. It's just like, oh, hell yeah. So sine x squared, or sine theta squared, is just sine theta sine theta. So if we want to take the derivative of this with respect to theta, then this is your u, this is your v, and you're going to go, the derivative of this is the first times the derivative of the second, dv d theta, plus the second times the derivative of the first. And let's do this to finish out. Because what's the derivative of sine theta? Well, we know sine theta starts at a 45-degree angle, basically, if you're in radians. It's a slope of 1 right off the bat. And well, cool. So derivative is an equation for the slope. So at an x value, or a theta, oh man, yeah, at an angle of 0, is that what they say? So when sine is 0, we have 0, but our slope is 1. You know what I mean? So if we go to sine 30, hell yeah! We go up to 0.5, and so this is literally sine 0.5 in radians is 0.5. It's a 1-to-1. So that literally shows you have a slope of 1. So what equation, when you throw in 0, gets you 1? Well, it's cosine. Cosine of 0 is 1, and that 1 is the slope of this graph. So when we go u, we're going to go sine theta. Derivative of that is going to be cosine theta. And then we're going to add it to this sine theta, and then the derivative of that is cosine theta. Heck yeah. And maybe you could simplify this, because you have sine theta, cosine theta. And I might be just telling you totally wrong. I might get this wrong. I don't think I am. But now I do know there's a half angle relationship with sine theta, cosine theta. So 2 sine theta, cosine theta. Hey, that's what we have. 2 sine theta, cosine theta. So that's going to be sine 2 theta. So we have sine 2 times theta. That's the derivative of sine squared. Now, is that true? Is that true? Because we can just do it right now. We can say sine squared of theta, and if we want to find the change of it with respect to d theta, how do we do this, that makes it make sense? Well, let's throw in 0 and evaluate sine squared theta. That's going to be 0. And then we're going to evaluate maybe 0.01. So we're going to go sine, and we'll go into radians. So sine of 0.01, and then we're going to square that. Well, let's just do sine of 1. Sine 0.1, and then square that. So we're going to have a change of 0.00996. I'm going to store that as x. And then what did we change our theta? Well, we changed our theta by 0.1. So now this becomes, that's like multiplying by 10, so we get 0.0996. And then what's the sine of 2 the change in sine theta? Oh, this is interesting. I don't think I have this right, but what? Sine 2 times 0.1. Let me not end on a horrible note and then go look this up. Alright, hell yeah. So we're back, and man, that sucks, because I totally did not know what the graph of sine x squared is. So here's in Wolfram Alpha, this is sine x squared, and so right down here is that, yeah, you have a, and that makes sense, because, hey, look how this goes negative. Well, obviously it's flip-flopped, and then you don't have an abrupt edge, with sine x squared. You would just have a nice little transition, and then so you do have zero slope right there. And you know, if we want to kind of prove that, you know, you just do, hey, change this d, like the whole derivative thing. It's like, hey, change it a little bit, sine x squared, change that with respect to x. And then so we're going to go and let's do it in degrees, because degrees will help us out. So we're going to do that same thing, sine 0.001, and then we're going to square that, and then we're going to store that as x. And then so we're going to have 3 times 10 to the negative 10 divided by, we just changed x by a thousandths of a degree, but this is 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros and then a 3 divided by 0.001. So visually this slope is 0. And so sine x, yeah, we showed that the derivative was sine cosine plus sine cosine, or just 2 sine cosine, or by that identity it's going to be sine 2 theta, you know what I mean? And so so there you go. But yeah, that was brutal in such a weird way to end it. But no, that's good, because it goes back to be like, what is a derivative? You know what I mean? Well, the equation goes in there. You're changing the equation just by a little bit, and then you're seeing how much it changes compared to how much you actually, you know, this is your step. For every step you took, you know, did it change a lot? Is that number bigger, or is that number like considerably smaller in proportion to the step you took? And if these are equal, if the step you took is equal to the change, well, then you have a slope of 1. So at some point between, well, I don't know, you don't have to have a slope of 1, but I mean, even just graphically, that looks like a slope of more than 1. And then 0, and then more negative 1. Okay, so I think I'm done with this, and who knows if I'm going to have an addendum of how to solve this. I don't think so. I think I'm just going to post this video, even though it gets just a little bit haggard at the end. But we did learn about derivatives, and I don't know. That's why I'm not going to post a beginning to this, because I just can't think of a very smart way to get there faster. Yep, so I'm just going to end it at that. We did some derivatives. We did sine derivative of sine x squared, because we used the product rule, you know what I mean? And again, sine x, what's the derivative of it? Well, you're going to have a u and a v, and like they say, it's the first times the derivative of the second plus the second times the derivative of the first. Cool. All right, with that, I'm out.